हेलो।
पाठ पाठक है। पाठक कितना बैटरी फुल दिखा रहा है ना। अभी देखना पाठक, दूसरा भी। ठीक है।
अभी चालू किया है.
Hello. Hello. A very good morning to one and all. I'm Supriya Bhide, a PhD student from the Plateau Group, and I'm here to take you through the day's proceedings. From powering tiny calculators to propelling humanity into space, the realm of programming languages and compilers has continually pushed the boundaries of innovation and possibility. If you have softwares doing shiny things on the screen, rockets launching satellites into space, we have backstage artists, the compilers, who've made this possible. And just like the plight of backstage artists, the fascinating trends or developments in the field of compilers and programming languages do not easily gain the limelight, and the students remain oblivious to what's happening in the industry. Well, we always have been told by our professors that interesting things are happening in the industry in the domain of compilers and PL. So we thought we'll confirm it from the industry delegates themselves. And Placid 2025 is our opportunity to do so. With this, we welcome you all to the second edition of Placid, or Programming Languages and Compilers in Industry Day. To commence this momentous occasion, I would like to invite Professor Uday Khedkar to grace us with his welcome address, setting the tone for what promises to be an inspiring and enlightening day ahead.
Very warm good morning to all of you. It's a great pleasure for me to welcome you to second edition of Placid. We started this tradition last year and we found it to be very, very satisfying. Let me share with you some of the thoughts behind arranging this event. The main motivation behind this event has been to answer some of the questions from students where they would wonder that the compilers exist for all languages and we have Gen AI writing code for us. So why should this subject be taught at all? And this appeared like an existential crisis for someone like me who has been in this field for over 35 years. So we thought that maybe we should bring it to the notice of the students that some very interesting things happen in this field. So Placid is our attempt to answer these questions. The idea is to tell students that yes, there is a lot of information available on internet in Gen AI, but the reality is the right way of describing it is like when you get all this information, you are absolutely free like lost ships in the sea. So you need something that will help you find your coordinates. And the Placid event is one such attempt where we talk to the people from the industry, we hear from them what they're doing, and that allows us to find our own coordinates. This is for the students and for us teachers and researchers as well. The way we personally look at it is that this is an attempt for us to recalibrate our ideas against the ground truths, because we have to keep ourselves aware of the ground truths. So to the delegates, we are truly honored that you're here. You have taken a couple of days off from your rather busy life for us and for our students. This means a lot for us, and we are grateful to you for accepting our request and contributing our process of recalibration. I hope this will give you a glimpse of the quality of research and teaching that we do, and that you will be able to find some people who will join you not just for the salary or stock prices of the company, but for the love of the work. That is the reason why we have here a mix of multinationals, Indian companies, and startups. To the students, and I see very few of them, I hope they will wake up soon and come here, certainly before lunch. So I do hope that we will have this auditorium full by then. But to the students, please make the most of it. These people are here for you. You will get to know what awaits you in real life, as they say, what we are preparing you for. I sincerely hope that some of you will join the community. Should that happen, I promise you that an exciting journey awaits you, which will enable you to find meaning and purpose in life, and also help us in perpetuating this effort. And one last piece of advice to the students, please show your name badges at the food counter. We have opened the event for the people who have not registered, but the food is available only for the people who have registered. To the folks who are attending online, and yes, this is one of the new things that we have done in Placid. We had close to 75 people who had registered online. I do not know how many of them are online right now, but I welcome you all. Welcome to our tiny trusty world. This year we have extended Placid to include you people, but the interaction is still one way. Based on the experience this year, we will enable a two-way experience. How is Placid different from last year? Well, it's spread over 1.5 days. Last year we had only 1 day and we felt the schedule was a little cramped. So it's spread over 1.5 days. There are more talks and much more free time for interactions. We have moved the poster session to next day morning, and then there are breakout sessions with the industry where students can talk one-on-one with the industry experts. So with this, I once again welcome you all to Placid, and we will get started with the talk. One of the things that I would like to emphasize is that we would like to maintain the time. We would like to begin on time. We would like to end on time. We would apologize to the speakers in case we have to show you how much time is remaining. We'll tell you when 5 minutes are remaining. We'll tell you when 2 minutes are remaining. Please keep looking at me or Manas so that we don't have to come and show you in your face. So please make sure that everyone gets sufficient time. Let's begin on time and let's end on time. So let's enjoy this event. Although the event is named Placid, the happenings need not be calm. They should be energetic and enthusiastic over the next 1.5 days. So welcome to Placid. Thank you.
Thank you, sir. Our first talk is from our esteemed delegates from Qualcomm. We have Mr. Sushim Srivastava and Mr. Pankaj Gode. Mr. Sushim Srivastava is a seasoned expert in the wireless semiconductor industry with nearly 25 years of experience, including 19 years at Qualcomm. Starting as a 3G protocol stack engineer, he has worked across 4G and 5G compilers, cloud computing, machine learning, and software security. He continues to drive innovation in the field. Please welcome Mr. Sushim Srivastava. Mr. Pankaj Gode is a staff engineer at Qualcomm. He contributes to LLVM-based internal toolchain for Qualcomm's modern processor with target-specific compiler optimizations and toolchain enhancement, and has worked on Qualcomm's ARM64 server processor for data centers. Please welcome Mr. Pankaj Gode.
So meanwhile, the things are getting set up. It's very interesting, though. Call we can give to him, yeah, and I will use this one. So he talked about the attendance. In my view, it is huge. For grad level talks, I have even spoken to 3 candidates in the hall. So it was auditorium full. I'll not name the institute, but there were only 3 students. And it was interesting, I think at that time, somebody pointed out, so we were looking at making compilers more interesting among students, and we were doing grad level talks. So one of the professors told us, guys, you are preaching to the choir. They're already in compilers. So then we started some, talks around why compilers and why we should pursue that. That's not agenda today, but that's how we started speaking. And in those talks, we started getting more and more audience. But the grad level talks, oh, this is a huge audience. This is a huge audience. Okay. So we changed our plan based on Uday sir's guidance and the emails, because he said that people should be able to take back open areas or what's going on as the current research. So earlier our slides were around what we have done and what are the results around there. We'll still show some of it, but we'll mostly speak about the open areas and challenges which we are facing, which industry, research community, everybody is facing. And we are told Manas already that as soon as our time, we are close to time, let us know, because open areas we can keep speaking for very long. I'm audible, right? This mic.
We are just waiting for the slides to show.
Okay. So still, I'll continue because this doesn't need slides. Open area doesn't need slides. We'll put it there. So we'll start with the ML compilers, because there are a different set of challenges, and advanced topology, we both are run from the traditional compiler world. So ML compilers, we are still the new learners. So we'll try and talk about the challenges. So shape challenge. When we use the word shape among the student community, are you aware of what shape we are talking about in ML compilers? No. Okay. Because I'll retreat into the basics based on that. So shape is the shape of, like, when you see a data set, you have a lot of independent variables, x1, x2, x3, x4, x5, x6, x7, and so on and so forth. And then you have independent variables and the dependent variables, which are the output. So shape is the shape of tensor, how many dimensions it has, and the problem with the shape of variable, you can use the word if everybody is not comfortable with the tensor. So if x and y are there, you are in 2 dimension, you are giving input in x dimension, output is coming in y dimension, it's a linear. When you go to x, y, z, 3 dimensions, so x and y are the inputs and z you are getting as an output. So more now this shape is not static. So when you do traditional compiler optimizations, you know what that variable is. It's a float, it's int, it's size, it's everything. Like, it's more or less static. In machine learning, the shape of the tensor keeps changing. So how do you optimize when the shape of the tensor keeps changing? So there was one solution. Let's take the static size of the shape. But when the static shape of the tensor, but then what happens is the shape changes, then you need to recompile, and the frequent recompilation will be an issue. So critical because they are able to predict the shape speculation, is able to predict the shape of the upcoming tensor quite effectively. And there are certain patterns are more frequently in the shape of the tensors as compared to, maybe 80-90% of times, I'm throwing that number, I don't have the number right now, the shapes can be predicted. So these are the methods which are people are using in the kind of optimizing the shape problem. These are the three major problems or four major problems I will say in the case of ML compilation. Number one is shape, number two are loops, number three is sparsity, and number four I will say the dependent ops. Like, what do I mean by dependent ops? Is like, let's look at the LLVM IR or any IR. So at that level, you don't have information about if two ops are dependent on each other or two ops are running simultaneously or some other dependencies. So you need some information on dependency of ops among each other. You need a higher level abstraction. So that was an important requirement in machine learning compilation. Since the slides are up, I'll speak about something about slides because I just got started on the shape because slides were still coming up. I hope shape problem is a little bit clear because we are going to cover a lot of problems and we are trying to give you a starting point. We cannot cover the whole literature review on a problem statement in this time slot. So another thing is, while I move to the next open area of ML compilation, I'll speak about specifically our challenges. Our challenges means the people coming from the embedded devices company. So when you talk about open areas in compiler domain, mostly you speak about the GPUs and CPUs, and then you see a lot of problems already solved for GPU and CPU. Believe me, those solved problems on GPU and CPU, we are not even scratching the surface in the constrained computing or the embedded world. Pankaj programs for or writes compiler for one of the microcontrollers where the memory budget, the total memory budget is 1 MB and the processing power we have, compute power we have is 840 megahertz. So, for example, we were working on a sanitizer work, UBSAN? Yeah, undefined behavior sanitizer. And then the problem is solved for, the normal compiler world. But for us, if we use the same solution, the bloat in the code size is 300%, which is unacceptable. So there are a lot of constraints which comes to our, every byte of memory counts. So that makes everything much more complexer. Especially our most of machine learning processing happens on a DSP, which we also call it neural signal processor, but is actually DSP in an underlying structure, and DSP comes with its own limitation. It can do some control and some parallel processing, but not parallel processing not as comparable to a GPU, and control not as comparable to the CPU. So we have our own challenges. Moving on to the next problem statement or the open area in ML compilation is loops. So when we are solving the loops problem in traditional compilation, we generally know the feature of loops, we generally know the heuristics, we can derive the heuristics. The loops are not as complex as in the machine learning world. So how we are looking to solve the loop problem in machine learning world, we are mostly going to the polyhedral geometry or polyhedral compilation framework. And we rely on parametric polyhedra to represent programs, especially those involving nested loops and arrays. Again, I'm most likely throwing a word which a lot of people may not know from the student community. So polyhedral compilation is a very, very interesting domain, especially for the loop optimization. So if you are interested in that area, look at polyhedral compilation. It's a very, very interesting area. Then what happens is, in case of the loop compilation for machine learning compilers, it becomes more interesting to use machine learning for the loop optimization, because you are not able to derive the features easily, you are not able to get the heuristics easily, the shape of the various tensors might change. So there is a lot of work, especially like if you, Monsifrot et al., there is one paper which I found very interesting on the loop optimization. Then there is one by Stephenson and Amar Singhe. So you can look at that. They are using machine learning to optimize the loop optimizations in case of ML compilers. The advantage of machine learning based approach is if we do them right, we might be able to, for example, when you do loop optimization, one of them is unrolling, and there are many more loop optimizations. We do them based on heuristics, and we do them standalone. Using machine learning methods, we can do loop optimizations, which might be applicable to different hardwares and can be ported to different hardwares if we have those heuristics or training done well. However, the challenges remain again here. The open area is creating the models which can optimize different hardwares, and we can use the transfer learning or other methods to run the same loop optimization for the different hardwares. So it's again a very, very open area, loop optimizations. A critical challenge applying machine learning to loop optimization is developing effective representation of loop structures and their characteristics, which is also called as feature engineering, the process of extracting and selecting the relevant program features. I moved back. You're able to hear? Yeah. Something to say? Both. Oh no, so this is for my notes only. This is for my notes only. So what are the features of a loop? The process of selecting relevant program features, including metrics such as number of basic blocks, branches, instructions, and more detailed characters like every instruction level. So, yeah, I wanted to speak about polyhedral, but I don't think so. There will be a lot of people exposed to polyhedral. I will leave polyhedral. Jumping from another. No, they put the column right now. Yeah. I know there is some part required from our side where few institutes are already working on, where you will have a DSP architecture courses. So we are okay? Okay, I'll be a little louder. Even mic, then, oh, the mic is there. So these challenges, when we try to do machine independent or architecture independent loop optimizations, using like machine learning to optimize the loops, are like different challenges like connecting the sufficient training data for new architecture, learning algorithms that can transfer knowledge from one architecture to another. The development of transfer learning techniques specific to compiler optimization could significantly advance the field, because this has happened even in the traditional compiler optimizations, where we have, let's say, done an optimization of on our DSP, and to port it to the microcontroller or port it to ARM or port it to RISC-V, we required to generate the new heuristics and do a lot of work again. Though it was faster, let's say the first processor took 6 months to do that optimization, the next one we could do or transfer the learning. Again, a task. If it is those optimizations, that will be interesting. So, in summary, if I say the for loop, what I have made my notes here, they are my handwritten notes. So, for sequential program, there is extensive work in predicting compiler flags, codes, transformation option, or tile sizes for loops. However, directly predicting optimal options for parallel program is more challenging due to complex interactions between. We are like, you would have read the news, CMU is running a LLM on edge on a DSP by using quantization. So when you run the large language models or the Gen AI models, it's basically graphs. And graphs, as you know, are very power intensive and memory intensive. So if you could transform, there's work going on transforming graphs to loops, and once you've transformed them from graphs to loops, but this is more radical, but though, there's work going on this. Once you transform them to loops, then it is very easy for polyhedral compilation methodology to, optimize those loops. Sparsity, very interesting about sparsity is, I hope folks know about sparsity. This is the ML world. Students should be aware of sparsity. Like all the data is not available. Some data is missing, available. So hardware's, so sparsity, rather than treating that as a problem, if you look at MLIR, they are treating sparsity as a feature. So accept sparsity and work on it. There is another interesting area is like one of the hardware companies have built a hardware specifically optimized for training with unstructured weight sparsity. So there are work going on in sparsity area Compiler need to generate different code based on target hardware's capability for handling sparsity. Research is needed to develop abstraction. Like LLVM IR or any other IR, we have lost a lot of information about if two ops are dependent on each other, two ops are running simultaneously, two ops are running together, or multiple ops are running together, or this ops run after this one, and the dependent ops information. So we needed another level of abstraction, which MLIR provides quite nicely. So dependent ops was another thing in ML compilation, which was not very easily done in traditional compiler systems. So if you is like this is again in my personal view that MLIR is the way to go, because there are a lot of hands on the deck and a lot of people are then lineage. Hexagon is like what we are specifically doing for DSP, because most of the dialects are looking at the GPUs, CPUs, and other processors. So Hexagon dialect is coming in to support the DSP, and then we go from there to LLVM dialect and LLVM IR. Once LLVM IR is there, then the other system. So some challenges which I see, these are just starting points. I request the go into search those papers, do the standard literature review model, reading those papers, because your Gen AI might hallucinate, might I tried this even the deep research model of OpenAI. I asked the similar questions on, I spoke on what are the open areas in these. But what happens is those 30% with the misdirection you get, that is good enough to take you off the track for that one. So since the last 5 minutes are remaining, we'll quickly cover another interesting topic. I have something remaining for ML compilation. We'll continue tomorrow. ML compilation and hardware. I'll bring one more very, very interesting aspect in quick 2 to 3 minutes. Is proprietary hardwares with proprietary ISAs. These changes, and then I was looking at Hennessy Peterson. It advises us to do what we have done. So it is not even a paperwork. So what happened is, generally hardware and software, though the co-design word is very common, but they operate a lot in isolation. So people design ISAs, proprietary hardware, proprietary ISAs. So what we did was, for our proprietary hardware, we moved to an open source ISA. So how it helped us, or how it can help anyone, is once you move to open source ISA and you try to you just change the decode layer of the instruction and move it to your proprietary hardware and make your specific changes at the assembler level or upstream some extensions into the open source. Now what happens is, since our instruction set is compatible with RISC-V, any optimization coming for RISC-V, we are getting it for free. because our specific work starts from assembler. So code, then it's not research the way I was talking about ML compilation open areas, but very interesting way to get efficiency out of it. Like if you are in a proprietary ISA, any optimization you are doing, your team is doing, there are 6 odd hands or 3 odd hands who are 4 odd hands who are working on that problem. But as soon as you move to open source ISA, there are tens and thousands of hands all across the globe optimizing it, and you are getting it for free. Right? That's the summary. The Pankaj is the right expert. I'm imposed. Any question? I have many more things which we can discuss tomorrow in the interest of time. I just tried to discuss some open areas. You can discuss with us in the breaks tomorrow. Questions?
Hello.
Yeah.
Very good morning. Well, for certain optimizer shapes are never certain. The tensor shapes are not certain. So I wanted to ask, because whenever we use, if we use ML for a transformation, it wouldn't be, I'm assuming it's not necessary that the semantic equivalence is guaranteed between where you start and what you end up with after the transformation. Like, they may not be semantically equivalent because you're not using a deterministic algorithm. If that assumption is correct, then I'd like to know, is it then possible to formally verify if tensors of arbitrary shape are being transformed correctly?
Okay. There is a very interesting part in your question, because those are also, those verifications are also open area.
I see, yeah.
We have not worked much on the shapes, shape optimization using ML, but we or even loop optimization, we have not used ML much yet, but we are working on it. Using shape speculation, they are working on some work using ML for compiler optimizations. In loop, there is a lot of work going on, but I'm not aware of exact what optimization they are doing using ML for shape speculation, but I'm aware of some work is going on in that direction.
All right, okay. Thank you.
Also, MLIR has that as a primary thing.
Yeah.
So they are taking care of, so these are the primary first class areas which they are taking care of in MLIR. So one
I
is
see.
the, like dynamic shapes.
Okay.
So we are, what we are trying to do is we are trying to analyze if we can change with some optimizations handling those shapes correctly.
Okay.
So, but this is again work in progress.
Yeah,
Again,
got
2
it.
years.
And verification definitely is a big area. What you have done, what transformations you have done, are they valid? Are they not valid?
Yeah.
That's I think verification is a big open area in AI world. I think Professor Supratik is working here on neural verification, and there are many more people working on the neural verification. So yes, that's an interesting area.
Thank you.
So you talked about the low optimizations. So you're talking about the NPUs. So the normal issue with the GPU or loop optimization is that we have barriers, and it may lead to divergence, which can be very scary scenario than CPUs, because we generally use busy weights in normal CPU targeted programs, but because of barriers. So will not complicate the loop optimization from the CPU world?
GPU we are not working on. GPU, we work on DSP.
Only
NPUs.
DSPs.
No, it's okay. So not directly targeted to GPUs. Okay. Yeah.
And we have limited knowledge about GPUs. We only work on DSPs. Because our any one image, that amount of power, this runs for 30 hours. So for us, we talk in milliwatts. Sorry, GPU we are not much aware of.
However, in the DSP, I think we handle the loops very efficiently, because in DSP you have the concept of packet. So
Yes.
there the packet formation is such that you are taking care of the loop carried dependencies.
Thank you. I hope I leave a lot of keywords for your literature review search. That was my goal. Because what we solved, how we did it, it wouldn't seem very obvious, whatever one problem we picked up. And thanks to Uday sir for setting up the tone that talk about open areas, even if one thing clicks, that's good enough. Thank you.
Thank you so much, sir. Thank you for talking about the various challenges in this field and showing us a plethora of open areas in the world of compilers. I'm sure it must have sparked some great interest and thoughts among the students. Sir, I would like you to be here. Yes. So I would like to request Professor Uday Khedkar to present Mr. Sushim Srivastava and Mr. Pankaj Gode with token of gratitude.
अभी पढ़ रहे?
Thank you, sir. We now have our next talk from our eminent delegates from AMD. We have Mr. Praveen Jagtap, who is a member of technical staff, software development engineer at AMD. He is working on the GPU compiler features of AMD GPU, performance aspects, and the compiler toolchain related issues. He has a prior experience of working with the machine learning language and compiler team. He specializes in parallel algorithms, compiler development, and performance optimization, with prior experience as a GPU compiler at MathWorks. Please welcome Mr. Praveen Jagtap. We have Mr. Akshat Oak, who is a software engineer at AMD and works on the GPU compiler backend. Prior to that, he interned at IIT Bombay with our group. He is a recent graduate from BITS Pilani, Hyderabad. So let's welcome our youngest speaker in the house, Akshat.
Hello, can you hear me? Yeah. So welcome everyone. Thank you for joining us. We will take you through journey of how LLVM code gen looks like for AMD GPUs. So these are the contents for my talk. We'll start with how AMD GPU compilers looks like. Then we'll get into the typical day-to-day work for us. Then we'll spend some time understanding how the programming and execution model looks like for AMD GPUs. And then we'll transition into series of projects, thinking that you will understand, what we're working on, and so we will look at a lot of examples. Now, this is simplified view of our AMD GPU compiler stack. So users writes HPC applications using HIP. HIP is a higher level programming language which allows users to write compute kernels which are offloaded on AMD GPUs. Now, this HIP runtime lowers this compute kernels into LLVM IR, and after target agnostic LLVM IR transformations, AMD GPU backend lowers this LLVM IR to machine IR and performs target specific optimizations. And finally, backend lowers this machine IR to AMD GCNISA, which is then executed on AMD family of GPUs. Now, this stack also enables interaction with other programming languages like graphic shaders. These are also lowered to LLVM IR and share the same stacks. Modern deep learning applications developed using different AI frameworks are eventually lowered to LLVM IR. AMD's ROCm platform provides libraries for these frameworks, which are eventually compiled through the same stack. So, as a compiler engineer, you can imagine what kind of impact you can make on accelerating these applications. Flang and try to run reason buzzword, they also eventually lower to LLVM IR. So, as a compiler engineer, when you are working on the lower stack, everyone will get benefited anyway, right? Now, coming to the nature of our work, the entire compilation stack that we discussed is fully open source, including even ISA manuals. We have philosophy of upstreaming first and then including it in ROCm releases. We prioritize software hardware co-design by collaborating with entire ecosystem, including software, hardware, and even all the tools around the compilers. Our team is actively involved in proposing enhancements to industry standards like OpenMP, OpenCL, Dwarf, SPERV, and even LLVM. We also work on supporting future generational hardware features in a compiler. And work also involves addressing aspects like function call ABI, kernel launch ABI, and device to host IO. Now you can collaborate with us using LLVM PRs and GitHub issues. Now let's talk about the programming model and execution model of AMD GPUs. Now this is very important because on every slide I will be referencing this. Okay, so you can see here we have 3 functional ALU units. One is SALU, VALU, and matrix core, and 3 classes of registers: HGPRs, VGPRs, and AGPRs. Okay, now SALU mainly maintains the state of HGPRs, and VALU maintains the state of VGPRs. Now, Wave executes a program on 64 data streams in a lockstep fashion. So each of the stream is called as lane, and each wave gets its own program counter. Now, people who are coming from a CPU world, for the sake of this presentation, just assume that this wave will be executing all the programs that I will show you. So it's very easy to understand the challenges that we will be talking about. So on GPU, since GPU are ultra-wide SIMD machines, there will be a lot of waves doing context switching at the same time. Okay, but for sake of this presentation, we'll focus on only one wave execution and one instance of a program. So as name suggests, VALU executes vector instructions on 64 data streams or all the lanes, and SALU performs a single operation across all the lanes. And then you can see this VGPR holds a different or divergent value per lane, and HGPR holds the same value that is across all the lanes. And exec mask, which is another important aspect. So we have some state variables which kind of controls the state of a wave. Now exec mask kind of controls which lanes of the wave are active and which lanes are inactive at any program point. Now we'll see how this translates into a simple program. Now again, imagine wave is executing this program. You can see some vector instructions, some scalar instructions. This will be using this VALU and scalar ALU units, and some VGPRs and HGPRs. Now this variable C is mapped to HGPR1 because it holds uniform value across all the lanes of a wave. Whereas variable X is trying to load a different or divergent value per lane. That's why it is mapped to VGPR1. And variable Y is clearly divergent value because it's adding one SALU and one VALU value. Now, if you look at this representation, what we are showing is all the lanes are active. That's why these computations are triggered for all the lanes. And exec mask controls which lanes are active and which lanes are inactive at any program point. Okay, now we'll talk about how do we handle control flow, for the programs, input programs. Now, why structurization required is mainly because LLVM does not provide a way to represent wave-like execution. We'll see what I mean. Consider this simple program with a divergent if-else condition. Now you have in the CPU world, what will happen is if you look at the control flow, it's a classic diamond pattern. At any point in time, if you look at one execution, either you will execute P, Q, and R, P, Q, and S, or P, R, and S. Even if you launch multi-threaded application with parallel programming models, if each thread had its own PC, it is possible to perform Q and R at the same time. But on AMD GPUs, we have PC per wave. That means we cannot perform Q and R at the same time. So instead, we have to trigger computation for some lanes and perform no op for others. That also means your wave has to traverse through all the basic blocks. Now, we take a when wave is here at P block, and we know we have a divergent condition, so we have to trigger a computation only for lane 0 and perform no op for others. Right? So eventually, you will see this wave will traverse through an entire basic block. So the first thing, before even reaching to a backend, we have to restructurize a given program for target like AMD GPU. Okay, now the current structurizer that we have is looking for entry and single exit patterns and not the entire function. So we have seen cases where this can be done in much better way. So there is already work in progress where we can optimize addition of these flow blocks, because this addition of flow block kind of improves the lifespan of variables, and which in turn can increase the register pressure. So doing this optimally is very important for AMD GPUs. Now we'll talk about one project, contended global atomics. So this is an example where you'll get to know how we interact with hardware folks. So hardware team, they wanted to assess a low performance of global atomic operations. So they were looking for software, compiler, or runtime solutions to mitigate the effect of this slowdown in a compiler. And we'll see one transformation, that is AMD GPU Atomic Optimizer. It's an IR transformation. We'll look at how that helps us mitigate this effect. Now consider, again, Wave is executing this program. Now user wants to perform atomic update at this PTR, uniform PTR location by val amount. So the lanes of a wave which evaluates this condition to true will participate into this atomic update. Now if you look at this, I have just drawn 6 lanes and the uniform memory location. So each lane will come and take its turn to update the value. Now the question is, how can we optimize this? Now a simple approach to this is, we are performing per lane atomic update, right, in an input program. But we can combine this request into a single wave and perform wave-wide reduction. So this if loop is allowing only the first active lane of a wave to go ahead and update the value by, not val amount now, by wave-wide reduce the value. So that instead of performing this operation 64 times, we'll perform only once. But the only requirement to this is we need to rematerialize this reduced value, which is again wave-wide reduced value. So we'll only update once per wave, right? Now the question is, how can we rematerialize this value? Now on AMD GPUs, we have multiple ways to do this. The most simplistic case is when the value is uniform. Now how can we prove if the value is uniform or not, statically while compiling the code? So that's where the uniformity analysis comes into picture. Now this will help us understand whether given LLVM value is uniform or divergent across the lanes of a wave. Now if the value is uniform, then reduced value is just number of active lanes multiplied by uniform value. So you will get the reduced value in one instruction. But okay, now we'll just spend some time understanding and explaining what we are looking for. Now the current uniformity analysis is not designed for incremental updates. Okay, so in the AMD GPU backend, we are using it all the time, but every time we compute the analysis. But this is very expensive, and we are looking for the collaboration or work where we can have a mechanism to incrementally update the analysis. The tricky part here is, imagine you perform one transformation. Now one known uniform values can become divergent or can stay uniform. So you have to look at each transformation carefully and figure out what really is happening. So it has to be done for every transform, right? Now with that out of the way, imagine this value is not uniform. Then another simple solution to this is we can perform scalar ALU loop which iterates over only active lane values and performs the reduction. Exactly similar like a CPU thread, because we have SALU available on hardware. And this will be still much faster than performing a single per lane atomic update. Okay, but on AMD GPUs, we know that the most efficient implementation to perform the reduction is DPP operations. Now this DPP DPP is not new hardware instructions. It is just a new modifier which allows VLU instructions to access the data of a neighboring lanes at full throughput. Now this particular feature, or if you look at classic reduction tree algorithm, it puts some constraint. The first constraint is, that constraint is because we want to perform the reduction in log n steps. The first constraint is we need to enable all the lanes. That's important. And to reduction to be valid, every operation needs to have identity value. Now identity value means, imagine you're performing this reduction operation on, let's say, 63 lanes. Now we know that if you enable all, we have 64. What you do with inactive lanes? So we have to set some value so that the final reduced value is non-affected. So finally what you get is the actual reduced value. And we can do this using these data parallel primitives. Now, of course, when you come at this program point, what we have to do is we have to modify the exec mask, set the identity value, perform the DPP operations, and restore the original exec mask. Okay, because this exec mask respects the control flow. It is derived from the control flow of this if condition. Now I want you to focus on this particular pattern, because we'll be coming at this pattern, I know, many slides. You have divergent if condition, then you change the exec mask, you perform some operations. I will define what those operations are in the next slide, into a full, with a full wave. And then again, once the operations are over, you restore the exec mask. Yeah, these are some numbers. You can see what kind of benefit you see with a simple program, a simple optimization like this. If you consider, the execution time of this particular kernel with this setup, it takes 66 milliseconds. And if you just turn, and if turn out to be, if the value is uniform, you are almost speeding up the application by 66 times. And if the value is divergent, the SALU will be still 10 times faster, and DPP is still it will take as same time as the performing normal uniform value update. Now we'll talk about one important problem, that is what happens with the register allocation with the whole wave mode operations. So first we'll define what these whole wave mode operations are. Now we have seen, right, in earlier example, there are certain benefits that can be exploited by enabling all the lanes of a wave, right? And the operations that are performed with this unnatural exec mask are called as whole wave mode operations. And we have seen we will see two benefits. One we have already seen, that is data parallel primitives. And another place where this is beneficial is HGPR spilling. Now on AMD GPUs, we have HGPR values. Now imagine we can spill this 64 HGPR values into a single VGPR value by enabling all the lanes of a VGPR instead of spilling to memory, right? But to implement this, it is really challenging, and we'll see what kind of issues we will get into, in the next slides. Now, if you want to achieve this, you need to change the design the register allocation pipeline like this. You have to first allocate HGPRs. Now you have sense of how many spills you have, and then you spill them to virtual registers, because then you don't need to worry about whether free VGPR is available or not. And then you allocate VGPR, right? Now we'll take a look at how this whole wave mode operations looks like in an actual program. So we'll look at one example with whole wave mode operation and one without. So first we'll look at without, and we'll look at how execution, how the execution pattern looks like. Now this program is in a machine IR representation just before the register allocation, and we have two virtual registers. One is %0, %1. I'm just defining blue def and green def. Now what happens, and all the example will go through a same execution pattern where the first lane is active, when we reach the divergent block. Now at this blue def, your all two lanes are active. It will write blue color into both the lanes of the same VGPR. Now you hit a divergent condition, only lane 0 enters into this. So what happens? We will write this green def will write into a lane 0 of %1. They are distinct registers. %0 is different than %1. We are dealing with virtual registers. And finally, we have use of %0. Now, we will look at the same program with the WWM operations that we have seen earlier, right? Now here, the only difference is now this green definition is a WWM definition. Now, just run through a same execution pattern and see what happens. Now you have two lanes active, you are writing into both the locations. You hit the divergent condition. Now, these WWM operations can write into all the lanes of %1. Okay, so they are not respecting the control flow. This is unnatural exec mask, because we are overriding the current behavior of exec mask. Now, then when you reach at the use, you see the blue colors in both the lanes for %0. Now we are going to look at now we are going to look at two cases where we'll see how register allocator responds to this. Now the first case is when the live ranges are non-interfering. The live ranges are not interfering here because of the redefinition of %0. Now %0 is not used in these WWM operations. Therefore, it is not live in this region. And another example is interfering live ranges. The only difference again is there is no WWM, there is no redefinition of %0 here. Okay, so the liveness of %0 spans across the if block and it interferes with the %1. Now, just keep in mind, these are the sample representative programs of an actual bigger problem. Okay, these are just to demonstrate a problem. Otherwise, it's very natural to think there is no use of %1. Okay. Now, let's walk through this simple program. We are looking at before free elimination, that is just before array. Now, same again. you have both the lanes active. You write blue definition into the lanes of %0. You perform then here in this if block. The only thing is this divergent condition says that only lane 0 enters. But this WWM def can write into both the lanes. Remember, we are enabling all the lanes for DPP and for HGPR spelling. So, and we have seen benefits of doing this. So we are writing into both the locations. Now, when you reach here at yellow definition, it will write into the active lane of %0. That's why you see only blue color in the first lane, and yellow stays as it is. And this use is again coming when the wave converges at use %0. You see blue and yellow and blue color. Now imagine if we feed this program to register allocator, right? Then RA is free to allocate a same VGPR because live ranges are non-interfering, right? But now let's run through the same execution pattern where lane 1 is active and see what happens. Here, it's a common same thing. You are writing into both the lanes of okay. One difference here is registered allocator gave same register for %0 and %1. At this state, we know which register classes they belong to. Both belongs to VGPR class, right? So this program is just same. Only difference is now here we are dealing with the physical registers, and RA has assigned a same VGPR because live ranges are non-interfering. Now, when you hit the diversion condition, this WWM operation can write again into both the lanes. Now, at the end, again, now WWM operations are over. You are performing per lane operation. Now, only yellow def will write into first lane of a VGPR 0. And if you look at this use, now that use has become yellow-green, right? Means when wave reached here, you have already clobbered the value. Okay, so using WWM operations or using a same register here is not correct. It will yield to incorrect behavior. And simple workaround to this is, the extending the liveness of %1. That is here extending the liveness of WWM registers. Now with this, RA is now forced to give a different register. Everything works fine. Now this was working for some time until we hit into another case. Now we'll talk about that. Now what happens if the live ranges are interfering? RA is now forced to give different register. But consider a scenario where RA did not find a free register. Now it has to spill the VGPR 0. It is forced to spill VGPR 0 so that it can use in the WWM operations. Now with the same, again, if you hit the same execution pattern, you are seeing we are spilling active lane and we are reloading only the active lane. Now this will again lead into a same issue, right? Because the value is again would have been clobbered by the WWM definitions, right? So again, here also when spilling is involved, we cannot give a same register, especially when spilling is involved. Now we needed to split this register allocation pipeline into 2 phases where we allocate WWM VGPR first and then mark them reserved and allocate per lane VGPRs. Now this is not the long-term solution for us. We actually want to allocate this in a single pass because we don't want to, because they are not technically separate registers on the hardware, right? They are same. It's just that they happen to be, they are used in a different operations. So we are looking for a long-term solutions to, fix this issue. The only requirement here is all the RA infrastructure, including interface plotting, spilling, splitting, and even liveness computation needs to be whole wave aware. Now Akshit will talk about the new pass manager infrastructure that he is working on.
Hello. Yes. Yeah. So we have like 2-3 minutes. So Praveen talked about the optimization issues that we had. I'll talk about the overall compiler architecture issues that involve actually structuring all of these passes and analysis. So we have this sort of code gen pipeline for the backend code generation, where we have passes that are inserted by AMD GPU, like we saw atomic optimizer and uniformity analysis. These are part of the more generic pipeline that LLVM provides. Some of them are common passes like instruction selection or register allocation. And some of them are target-specific passes that targets add anywhere. Targets, by targets I mean architectures like x86 or AMD GPU MIPS. This is basically a series of passes that are structured together into the code generation that translates LLVM to machine code. So so to run this pipeline, we have something called a pass manager, which takes a list of passes, a set of analysis, dependencies between them, and schedules them together so that the correct analysis result is provided to the passes. Analysis need to be recomputed because passes may invalidate the IR, so the analysis may get invalid. There are two implementations right now for the pass manager. One is the legacy PM, which solves this as a scheduling problem. And the other is new pass manager, which solves this as a cache invalidation problem. Turns out this is much more better than the earlier scheduling approach, and we hope to gain some compile time improvements by using the new pass manager. Also, this will enable some easier interprocedural optimizations. Right now, the current state in LLVM upstream is that the optimization phase is already using the new pass manager. LLC, which is the code generation phase, is still moving away from legacy PM. So the challenges here are that we have to design this new PM infrastructure for the target specific code and also the generic part. So the hard part is that targets can add passes anywhere in the pipeline with arbitrary nesting, and so this is still in discussion with the upstream community on how to do this. And AMD GPU is on track to be the first target to enable NPM. With this, we expect some significant compile time reductions with compiling HIP kernels. Yeah, and that should be the end. Thanks. Yeah, any questions, Praveen, and I will be happy to answer.
Hello. Hello. Thank you for the nice talk.
Yeah.
So my question is not related to the talk. So, but do you know if any work where I can use? So you said LLC is very much implemented for GPU targeted programs.
It's not very much implemented optimally. Yeah.
Okay. So I'm saying, do you know any work which uses for LLI, targeted for LLI, LLM LLI?
Sorry, I'm not aware.
Okay.
Yeah.
I don't think we have LLI support.
Okay.
Yeah.
So that's currently there is no support like we have for CPU world.
No, I don't think we have JET support.
Okay.
For GPUs.
Yeah, we are from GPU compiler team. We don't, at least I don't know anything about CPU world so far.
Since there are no other questions, I can ask.
Yeah, sure.
Thank you. So I have a question. So I understood that the first part of your talk was about making multiple compiler analysis whole wave aware.
Yes.
And before that, you also said you motivated it by saying that, look, we work at the LLVM level and there are multiple things that boil down to LLVM level. And so anything you do at this level benefits everything.
Yes.
I was curious which application, I mean, is it mostly the AI applications or the MLIR kind of things or the traditional, which are the ones that are benefiting the most from these transformations that you're doing?
I am forced to say AI, but there are HPC applications. So I have one use case, but unfortunately I cannot show you. Actual use case where we worked with the Triton folks to provide them ability. So their claim was compiler is coming in between them. They want to produce this schedule, and the scheduler that compiler has is not able to produce the same schedule. Okay, so they write everything in assembly. You might have seen this DeepSeek, right? They want to have final control over the final ISA produced. But instruction scheduling on GPUs is very tricky because these are in-order machines. There is no speculative execution, right? So we run instruction one by one, and scheduling plays very important role. And we run 2 times. Before RA, we try to optimize for RP. After RA, we try for ILP. Both are competing objectives. Meeting them in production compiler is really tricky. So especially in last 1 or 2 years, we have seen cases where all these AI people, right, they come to us and say, okay, these applications are very slower, and if we write assembly by hand, it is doing much better job. So they can actually figure out what compiler is doing wrong. But in scheduler, one thing might work for their workload, but it may not work for other workloads. So doing this needs very rigorous testing, and it's tricky. But yeah, mostly AI applications, and there are some HPC applications, they also get benefited a lot. Even this atomic optimizer that we said, right? We first proposed it for only ROCRAN people, and they saw this performance, and then everyone started asking for, hey, we want this for 64-bit operations. We earlier supported only for 32-bit operations. So, I mean, everyone just now depends on compilers. There is nothing, which is not going through a compiler. I hope I answer your question. Yeah. Yeah, just one announcement. We have one position open for full-time and one internship opportunity. Feel free to talk to us.
I had a question. Aren't 64-bit operations on a GPU significantly different from 32-bit operations? Like, at least on the hardware side, I know that the bandwidth for 32-bit operations, such as floating point operations, is a lot more than things like double precision point operations, isn't it?
Yes, of course.
So what was there any challenges in compilation for 64-bit operations as opposed to 32-bit operations?
Okay, so simple answer is we compile for what hardware gives us. If the user wants 64, we provide 64. But there are recent new data formats like FP4, FP6, FP8, right? We have provided a way to new architectures like MI350. They have this lower data formats which are much faster because you pack them into a single vGPR and perform multiple operations at full throughput at the same 4-cycle speed. Yeah. We look at the type, and then based on that we optimize. But I did not fully understand what's the question.
Basically, I was just curious because from the hardware perspective, 32-bit and 64-bit are handled very differently in GPUs. So I was just curious if that's also true from the compiler level.
If user wants 64-bit precision, I don't think compiler can do anything.
Okay, that's all I want to know.
Yeah, it depends on the input program, I would say.
Makes sense.
Thank you, Mr. Praveen Jagtap and Mr. Akshito, for this intriguing talk. In fact, recently, register allocation and live range construction was covered in the class of Professor Ketkar and Professor Manas, and it was interesting to see its application in the industry. With this, I would like to call Professor Manas to present a token of gratitude to Mr. Praveen Jagtap and Mr. Akshito. Thank you, sir. For our next talk, we have our eminent delegate, Mr. Girish Punatil from IBM. Mr. Girish Punatil is an IBM Master Inventor and Senior Technical Staff Member at IBM. He is a key contributor to several open source projects and is a part of IBM Application Runtimes team that works on Java and Eclipse runtimes. He has authored a book on Node.js enterprise application development. Please welcome Mr. Girish Punatil.
All right. Good morning. Thank you, and sorry for the delay. Thanks so much for joining this talk. Really happy and excited to talk about evolving Java for the modern workload. Now, what is modern business and modern workload? It's almost evident from the last two talks, but let's qualify it better. Anybody who is not using ChatGPT these days? Okay, nobody. Okay, one person. Anybody still using Google search engine? Okay, few of you. Even I still use that. I go to the browser, then by mistake I go there, then immediately realizes, oh, I have ChatGPT, comes back. So that's pretty much evident that the modern workload, what we are talking about is AI, and the Gen AI is real. It came out of the research lab and started solving the real world business problems, right? That's the direction we are looking at. And another proof point is to ask the common man, see if they are talking about AI, they are. And these days even the farmers start talking about AI. So it's another proof point to say that that's where the direction is. And then $3 trillion is the investment that's happening in the next few years in this specific domain, which is huge, which is a massive percentage of the investment that's happening across the IT industry. So it's not just the research, it's the business, it's the enterprises that's investing on that. So this is where the direction is, this is where the whole programming and the effort of the engineers are being put. So there is absolutely no question about that. What Java is doing in that space, as we know, Java is 30 years old. By the way, we are celebrating Java at 30 in various formats through jugs and community meetups and other events. Please follow, if you're a Java lover, if you're a compiler programming language lover, please follow the activities and the celebrations to not only just be part of the community events, but also understand the evolution of Java over the years, how it made its best effort in terms of innovation to catch up with the trends and the latest and greatest in the modern workload scenario. So some of the things that I'm going to capture is a glimpse of what those attempts are. Last year in this same stage, I talked about how Java is shaping up for the workloads in the cloud. This year, I'm specifically talking about the AI workload. So my talk has three parts to it. One is what the language, the APIs are exposing the capabilities to the Java programmer for improving the developer experience. Then two, what the compilers and the virtual machines are doing in that space to improve the experience of the machine. And three, what the additional capabilities are built on top of it to make it more attractive to the enterprise and the business that is investing on Java. So let's start look at the premise first in how Java has come into existence and where Java is today. So I don't know how many of you will be able to relate to these premises. People who started developing in 90s will be very much able to see what this means. The first problem Java tried to solve is portability. At that point in time, we had heterogeneous types of machines, not like CPUs and GPUs, but systems that had different definitions of the bytes and the bytes order, different definitions of the network sequences. The very basic premise of computation itself was different for different systems. That's the time at which Java was born. But also lucky for Java, that's also the time when the enterprises started seriously looking at software as a way to solve their business problems. So Java proliferated by solving most of these problems. Some of the problems that the languages like C, C++ had at that point in time about the right level of abstraction. C was too low level, and Languages like HTML, SQL, they were pretty low level, pretty high level, but were domain specific. They are not general purpose languages. So you need a language which is sufficiently abstract so that developers can model the real world entities around pretty fast and still get the best benefit from the system. So Java was positioned in that space, and it was very, very easy for adoption with that level of abstraction. So you wanted a way to automatically garbage collect and manage the memory. You didn't want the pointers. People hated pointers at that point in time. And you wanted a cool way to actually manage concurrency, so on and so forth. So that was a premise in 90s. What has changed now? When we look at today, some of these features, cool looking features about inheritance, polymorphism, all the cool thing that we talked about Java, unfortunately has become pain point because when it comes to the workload that we are dealing with, none of these things matter. In 2025, when we are looking at the AI workload where you need to either do the training of a large data set or you need to make inferences from a model, foundational or fine-tuned model, what you need to have is extremely super fast computation power and ability to get out the inference as fast as possible. So the developer experience has given way to the machine experience in 2025. All what we need is the bare metal efficiency. Developer experience takes a step back. So the languages, the compilers, the virtual machines all have huge role to play, from translating the man's intent to get it to the machine's level so that things can run super fast. So Uday said we have a problem of existential crisis for the compilers. I would say the compilers by definition is to translate the man's intent to the machine. As long as there is a man-machine interaction, the compilers will survive, they will exist. That's my answer. This slide, I like it very much because we need that translation. Whatever the workload is, whatever way the direction is going, that translation has a scope always, and the compilers will have the job. That's my answer to that. And it's my conviction working in Java for several years, working between the compilers and the customers, I see that the scope is always there, but let's see some of these aspects. Okay, so how Java is evolving through the programming language interface. Number one in the slot is virtual threads. Traditionally, Java threads are just native threads, the thread created by the OS, and it has overhead, memory overhead, context switching overhead, scheduling overhead, and so on and so forth. Every thread comes up with a constant amount of stack, 2 MB, 1 MB, whatever. Whether you want it or not, that thread resource and the scheduling context is always an overhead. Virtual thread is a attempt to make threads in the user space, and with that, you're able to create millions of threads in the user space with super speed and efficiency with less resource consumption. Record patterns, as we know, Java doesn't use pointers outside, but internally it's full of pointers. So when it comes to a piece of AI data or any data, it requires 3 levels of pointer in direction. First pointer in direction is to get the Java object pointer to the business record or business data that the object is actually representative of. Second pointer in direction is to get to the actual location where the Java fields, object fields are kept. And the third one is, if it is an array sort of record, to get the actual data. The final star PTR comes through the third pointer in direction. So in the AI chamber, these things do not make any sense. You need to get the actual business data as soon as possible. So record pattern is an attempt to deconstruct the high-level objects and get hold of the direct records and fields at your hand. Vector APIs, again, the SIMD instructions and single instruction, multiple data instruction set hardware support was always available, but not many languages were exploiting it. Java JIT had an optimization, but by virtue of the workload through which Java was largely living through, it was not very much popular. But now SIMD become reality because you have operations that need to be performed across different data, the same operation. So it's like a lambda and a thread combination sort of thing. So we need to have a first-class API exposed to the user to exploit the SIMD hardware, the register set. Foreign function and foreign memory. As we know, the way Java interact with the native is through JNI, Java Native Interface, and it's notoriously inefficient by multiple means. Number one, the Java to C++ bridge requires two levels of protocol change, marshalling and unmarshalling. The Java objects need to be converted to a C++ or C object, so casting, and then need to be passed to the C world because C world understands only the C type. The second one, the Java code to the C or C++ code conversion requires multiple trampolines, gates, and call bridges, and so on and so forth. So when you are doing an inference, going through these levels of indirection, call chains, and all do not really scale up at all. So the answer from Java is to have the symbol, the native symbol from the TensorFlow or any of the native code that's running inside the AI pipeline, invoke that symbol as if it's a Java function directly. There is no marshalling, unmarshalling involved. There is no trampolines involved. So you get a direct feel about making a Java function call. So that's foreign function interface. CUDA4J and LangChain4J are attempts to model the GPUs and the parallel hardware in a sophisticated abstraction so that programmers can directly code for the parallel hardware rather than understanding, going to the low-level plumbing details and managing the concurrency by yourself. Provide a very sophisticated abstraction. Well, some of the things that we can talk about, brainstorm tomorrow, is also on these lines where how can we have a better abstraction, better programming model so that the code is natively running in the parallel hardware as opposed to some retrofitted algorithms or semantic models. All right, so those are the things that's coming from the languages, APIs. Now let's look at how the compilers and virtual machines are also adapted to the changing business needs. So the first one in this is off-heap optimization with a balanced GC. As we know, garbage collection is a cool word. It's a good attempt to, give a good experience to the developers. Last year in this stage, I talked about GC is not good, and people had a difference in opinion. This year, I am re-emphasizing on that point because GC has proven to be a bottleneck for the AI workload. When you are performing churns of operations through the neurons and the vector dimensions, etc., GC comes and stops everything. Doesn't really look good at all. So the question is, what is the right GC policy for this type of workload? And there is a huge amount of research that's happening. Ever since GC became popular, there is always research on GC, and that research is never going to end. The balanced GC is a best proven GC policy by which you cut the heap into multiple regions, and when one region is actually actively working on the workload, clean up the rest of the region. So it's pretty intuitive. But the problem balanced GC is offering is if you have a huge array, like a 2 TB array, and your regions are like half a TB or a 1 TB, you together have 100 TB of Java heap, but there is no single region where you can place this 2 TB array, because it's all discontinuous. So off-heap optimization is a way to place your 2 TB array in a native heap and still managed by the garbage collection in the Java space, so that Practical point of view, it's not in the Java heap, but in reality, it's controlled by the JVM. Instant on and instant hot. As we know, Java is notorious to start up slowly. There is reasons to that. You have class loading. It's a very, very slow process. It's a negative side effect of the bytecode, the platform independence, and all the cool things. It essentially means you need a lot of time to boot up the JVM by loading individual classes, verifying, stitching things, resolving the constant pool, so on and so forth. You also need to prepare the JIT and the GC to start kicking up. So all these things are happening at the beginning of the Java boot up, and it takes time. On top of it, you have the enterprise workloads. So by most of the micro benchmark means, it takes 10 to 15 seconds for the Java application servers like WebLogic, WebSphere, Liberty, Quarkus, JBoss, Apache, all these things take 10 to 15 seconds to actually start listening at the socket for the web workload. With instant on, what we do is allow the application server to stabilize, warm up, and then take a snapshot of the running process, like as if in a core dump, put it in the disk. And next time when this VM starts up, don't start from the process, from the kernel. Instead, get it restored from the checkpoint that we took previously. And we have seen that it's able to start up in sub-second latency, which is huge. So this is instant on is a technology from the operating system. We are leveraging that to get the best throughput in the cloud workload. Instant hot is an extension to that, by which we leverage the JIT optimization and the performing plans that JIT has executed in the previously running system, get the best out of it, and checkpoint it. So next time when you get a new VM, you not only get the fresh experience, but you get all the experience that the previous JVM gathered in a jiffy. So that's again a work in progress. Instant on is actually available in some of the web application servers like Open Liberty. Instant hot is still a work in progress. GraalVM and Quarkus is another way of solving the same problem, slow startup problem. We convert the whole of the bytecode into native images by compiling ahead of time and apply some of the optimization techniques of native function. So GraalVM is the basic capability coming from the virtual machine. Quarkus is a leverage of the GraalVM and providing the same capability at an enterprise grade application server level. So that's pretty much from the compilers and the operating system, compilers and the virtual machine perspective. Now let's look at one of the examples of how the other aspects of Java, more specifically Samaru runtimes, is addressing the needs of the enterprises. So FIPS 1403 is a specification for the federal use cases. In PR focus on European region. Healthcare has HIPAA and FISMA and so many other domain specific this one. And the difference is each domain focus on their specific area by virtue of what personal information they want to protect. When it comes to federal security, it's a union of all other security premises, because federal use cases store the personal data in its entirety. It will have the tax records, it will have the criminal records, it will have the immigration details and health records, everything. So what it means is FIPS security compliance require the best security posture, best security encryption standards, and everything that comes in the security domain. Whether you're a government client or not, if you care about your data and its security, FIPS 1403 is the golden standard for security at this point in time. JDK flight recorder. Now, with all this distributed computing and AI workload, one of the side effects is that you need to have observability. Previously, when you're running everything in one single process, you have a log server.log. You read through the server.log, you get the complete picture of the system. But with a distributed computing scenario, your application is distributed all across different nodes. So when something goes wrong, you need to have a cool mechanism to understand where things are going wrong, what it implies, where the root cause is, so on and so forth. So JDK Flight Recorder is a mechanism by which you capture the low-level metrics from the running VM and pass it on to some visualization tools so that you get a comprehensive picture of the server, what it is doing, and so on and so forth. So that's pretty much it is. Some of the messages or some of the learnings that I had over the period of time that I worked in IBM, working between compilers and customers, I said, is that languages and compilers do not exist in isolation. They evolve. They evolve to meet the needs of the enterprise, the needs of the folks who invest on the workload, and they mutate in that process. There is nothing called loving of a language. You need to love the logic, you need to love the creativity, the problem solving skills. Languages are all the same, or it will assimilate over a period of time. And when you're doing research on compilers or the programming languages, don't look at in isolation, don't look at in its immediate programming space, where look at the workload that it is trying to solve or it is trying to run on. Look at the execution environment in which it is operating. So that way you get a broader, deeper, and wider perspective about what are the different optimizations you can apply, not at the byte level, not at the bit level, but at the stack level. The whole software stack may be providing an opportunity. Most of the things that I talk about is not necessarily optimizing a loop, optimizing an expression. No, it's optimizing the whole stack. And still, as long as it's able to give benefit to the business, it's valuable. It's commercially valuable, at least. So, if you're interested, one of the other messages, so many projects are open. 80% or more of the business run today are all in the open. Even if you are a corporate, you are still using the open source technologies. So there is absolutely no restriction for you to embrace open. You can start looking at the projects, the opportunities out there, and the way you can contribute. Many of the projects you do have so many different opportunities, be it improving the CI/CD pipeline, improving the documentation, improving the performance, or providing various other community help in terms of supporting the language, supporting the community, so on and so forth. So there are different ways to contribute. Please seriously have a look at the open source as a way. It's not only just contributing the code, but also it provides a lot of culture, because open source developers are coming from across the globe. So you get a developer perspective by working and networking with people across the globe. So that's a very good perspective, I would say. Most of the things I talked about are taken from these resources. So the JEPs I'm talking about is all captured in one URL. All the Java enhancement proposals, all are in various stages of incubation. If you're interested, go have a look at that and start thinking in ways to contribute. So that's pretty much I have. Thank you so much.
Do we have any questions?
Sorry, it took a long time.
Hello. Yeah. So you talked about instant hot feature which you are using. So is that something somewhat similar to the idea of shared class cache, or is it exactly different?
So shared class cache is a way to share the classes. So why the class need to be shared? Because the classes are bytecodes, and bytecodes are intermediary representations that needs to undergo various stages before it can be actually executed. For example, bytecode verification, constant pool integrity check, so on and so forth. Now, if you can reuse the loaded state of the class in one VM as it is, serialized and deserialized in another system, that's what is class sharing. Instant on is a way to serialize everything in the process address space, not just the classes, the threads, the sockets, the running state of the application, everything, the memory, the stack, and the heap.
Okay, so if something changes, then how do you, is there a fallback?
Yeah, that's a good point. So instant on gives an API to the programmer to define what is your checkpoint. So the contract between you and the checkpoint system is that this is, you are taken for granted that this is not, anything before this is not going to change. This is the checkpoint stage. My actual production starts after this.
Okay, thanks.
Yeah. Of course, there are challenges. For example, in your application, you open a socket with a specific client, and that socket represented a $1 billion money transaction. Now, you are taking a checkpoint at that point and restoring in another VM. What happens to that socket? Is that still alive? Is the session is going to be repeated, and will the money again get transacted? So that's where the contract, the API contract with the developer makes a lot of sense. You don't checkpoint at that point. You checkpoint much before that, where you start the production. Thank you.
Hello.
Yep.
Thank you for the great talk. So I had a question that, as you mentioned, the workload is shifting towards AI applications, and there are some components which are creating hindrance to that. For example, JIT initialization and GC, which take roughly 10-15 seconds. So how do you approach to the JITs or the GC changes? Like, there's so much investment already made into the development of these things.
Yeah.
How do you approach for that?
Yeah. So that's a very good question. So there are several workloads which are still running. For example, web workload. All the optimizations, all the 150 optimization that runs in Samru JIT today are still valuable, useful, critically used in web workloads and cloud workloads. Just because AI is there, $3 trillion is invested, we are not going to throw away all those things. Plus, AI is there, AI workload is running in a specific deployment target. But that needs to be taken out. That needs to be interacted with the user. Input and output, all those things are still useful, right? It's not just the core of the AI engine that matters today. So everything continues, but you look at additional optimization options that will also harness this sort of workload.
Okay.
Yeah.
So based on the workloads, you filter what optimizations to be enabled and disabled.
Yes, that's a good question. So you may have to come up with different tunables. Say, for example, -X container that says this is going to run in a container. -X cloud, -X AI. It's not yet there. I'm talking about a future design. Yeah, there could be optimizations to automatically glean what is the type of the workload and auto-tune according to that as well. Yeah, but right now it's more about manual configuration. Yeah.
Okay. Thank you.
Thank you. Thank you, and sorry for the delay.
Thank you, sir, for such an intriguing talk and sharing resources. I'm sure it will be helpful for all of us. And thank you for emphasizing on open source. I would like to request Professor Uday to present Mr. Grish Punatil with a token of gratitude. Thank you, sir. And now it's time to spill some tea. Oops, I meant have some tea. So we shall have a break of 30 minutes. Snacks and tea have been arranged outside the auditorium. The doors at the back will lead to there. Feel free to interact with the delegates, relax, rejuvenate, connect. And please don't forget to be back latest by 11:25.
हेलो चेक हेलो चेक इसका ऑडियो टेस्ट कर जरा दीपक आ रहे का देख तेरे इसमें हेलो इससे अच्छा ना वही है कान वाला बहुत अच्छा है वो लगाने वाला हाँ हेलो चेक माइक टेस्ट 1 2 हाँ कम है ना इसको बढ़ाने में इसका लेवल बढ़ा थोड़ा लेपल का किधर
Welcome back. I hope you have refreshed and you're relaxed. Our next talk is by our esteemed delegates from Quadric. We have Ms. Samira Deshpande, who is a principal compiler engineer at Quadric, managing team of 6 compiler engineers globally. Their team at Quadric Inc. works on graph compiler and LLVM for their Chimera architecture. Ms. Samira Deshpande has contributed significantly towards establishing the GCC Resource Center at IIT Bombay. She has contributed immensely. She was a master's student at IIT Bombay. Welcome back to the campus, ma'am. We have Mr. Nilesh Shirsagar, who is a senior compiler engineer at Quadric. He works in the graph compiler and LLVM team for their Chimera architecture. He completed his BTech from COEP Pune and his master's from IIT Bombay. Welcome back to the campus.
Hi, good morning. I'm from Quadric and we will be talking about Chimera Graph Compiler. Ours is a startup, so you might not know a lot about our company. So I'll talk a bit about our company, and then mostly Nilesh will present his work that he has done in Chimera Graph Compiler, that is CGC. So Quadric is pure play silicon IP licensing company. So we sell the processor IP and the software stack needed to support that. We are on edge AI/ML inferencing architecture. The company was formed in 2017. We got our first silicon working in 2021 in middle of COVID. Then in 2023 we had our first IP delivery, and we have 28 plus patents granted both in software and hardware. We are based in Silicon Valley, venture capital funded company based in Birmingham. So this is us. Just 7-year-old, 8-year-old company. So you can count us as startup. But the work that we are doing is quite interesting, and I'd be happy to talk more about it because today we just have 30 minutes, right? So we won't be able to cover all the things that we are working on. So tomorrow, if you are interested in our company or want to know more about what we are doing, what we will be doing in future, please come talk to us one-on-one, and we'll go in detail about what our future plans are. So when we say that we are in AI/ML domain, what is the requirement for the chip? Right, so as we have seen in earlier presentations as well, we generally need a NPU accelerator for doing efficient ML inference, which are generally the tensors, so matrix operations. Then there will be a DSP for math kernel performance, which are generally vector operations. And then if nothing can be done in either of these two, then you need a embedded CPU for runtime subsystem or control transfer and everything, right? So now the problem of this is that there is a lot of communication and data movement is needed, right? So the solution is the Chimera compiler, which is inbuilt chip. It gives you system simplicity, programming simplicity, and it is future-proof because you don't now have to program for different modules, or you don't have to write different modules, different shaders, or to do certain computations. You can just write single program, and then it is the responsibility of the compiler to solve all your problems. It is future-proof because every time there is a new network coming out, the accelerator have problem because they have fixed pipelines. So that becomes problematic. And then they have to rely on the vector part or scalar part of it, which damages the performance. Chimera is future-proof because it is NPU, which is General Purpose Neural Processing Unit. So this is our Chimera NPU block diagram. It is pretty simple and all the architectures have it. But the main focus point for us and what gives the best performance is because hybrid of CPU and the systolic array that you are seeing here. So there are SIMD processing elements along with the scalar unit. So each processing element can be expanded further to have the local register memory, max, ALU operations, and then the data transfer and the data communication between each PEs, right? So now, only with this, okay, so before that, the number of PEs can be configured. It can be either 8 by 8, 16 by 16, or 32 by 32. We can have int 8 max per PE, or depending upon the data size, FP16 max are supported. And with that, we are scaling from 1 TOP to 864 TOPs right now. But even that is not sufficient enough. So Nilesh will be talking about the advancements that we have added in our architecture and how that is going to affect the programming model and what changes he is working on currently. Nilesh?
Thank you. Am I audible? I will be talking about our multi-core architecture. I will be describing what is the high-level architecture for Chimera graph compiler, and we will. Okay. Then we will look at a simple example how we generate code for our multi-core architecture, and how it can be used to take advantage of. To parallelize neural network workloads. So in this block diagram, we have 4 cores. We currently support a cluster of 2, 4, or 8 cores. Each core has L2 memory, its own array of processing elements, and also an instruction dispatcher. All the cores can operate simultaneously, and they can communicate with each other using this MLS or multi-core load store flows. Now I will talk about the high-level architecture of Chimera graph compiler. At its base, it uses TVM project framework. We first import a graph in ONNX format, and then we lower it to RelayR. RelayR is basically a TVM's intermediate representation to represent ops that are found in neural network. So then we have mapping optimizations, which map the TVM specific operators to our own architecture specific operations, such as, for example, TVM will have convolution operation, and we have our own implementation for convolution operation that is optimized to our architecture. So we will map that in the first step. Then we will have data layout assignment, which is basically like how we will represent the data in LRM, which is local register memory. For example, strided convolution and normal convolution will have different kind of representation internally in LRM, so as to optimize the performance for that specific op. Then we will have optimization at L2 memory level. Mostly, we cannot feed the entire graph in input, output, and all the weights and related data for computing output for any operation in L2 memory at one time. So we generally have to split it into different parts and bring it in as bring the data in as needed in L2 memory. After that, we have TIR passes. TIR is another lower level representation, which is basically a precursor to generating C++. TR operation, elements like statements in TR basically generally map one-on-one to C++ generated for that network. Now I will try to explain how the generated code looks like for a simple convolution operation on a single core. So suppose we have this input image. It has height and width 128 and 3 channels. This input image gets divided into regions of interest. Each region of interest is has height and width 32 and 3 channels. The height and width of region of interest depends on number of elements in our array of processing elements. Currently I am assuming the array of 32 by 32. So we will have each ROI will have 32 by 32 height and width. This is the generated code. First is the declaration for A2 memory tensor. Then we copy the input image from external memory to our A2 memory. Then we have declaration for output tensor. Then we generate loops to go over each ROI one by one. So during each iteration of this loop, we will read data from input tensor, perform convolution operation on it, and write result back to A2 memory. Now suppose we have multiple cores available. In this case we have 4 cores available. So 16 ROIs will be divided into 4 sets. Each core will get 4 ROIs. Here we are splitting the image, input image on height, but we can also split the image on width or both height and width. The choice of split type depends on the utilization for P array we are getting. For example, in this case, if we break the image such that each core gets 33 rows, then we will have 2 iterations for height because our array of P's is only 32 by 32. So in the second iteration, we will only be using one row at a time, one row of processing elements in that array. So utilization will be very low. So graph compiler basically tries to calculate utilization for all these split factors and then chooses the one based on maximum utilization. Next we have this code generator, C++ generated for this for multi-core architecture. Here we have a border L2 memory tensor because for convolution operation we will need to look at a 3 by 3 grid at a time and compute output for the center element. For example, for row 32 we will also need to look at row 33. So we represent this info by this representation 1100. So 1 refers to top down, first 2 numbers refer to top and down borders, and 00 represents left and right borders. So here we are splitting the image on height, so we only need top and down borders. For the here also we need to copy external tensor to L2 memory, but we are copying a distinct part of image in the L2 memory for each core. We represent each core with a core ID. So first core will get first 32 zeroth core will get first 32 rows, first core will get next 32 rows, and so on. Also notice that the shape of the L2 tensor will get adjusted according to like our multi-core split height. Here we don't have any iterations over height because we have only a single ROI in height on each core. Rest of the operations will remain same. So graph compiler has to perform optimizations in L2 memory size, adjust the offset for mem copy, and also generate the loops according to multi-core splitting. Next, suppose we have to execute 2 operations like convolution, one after another. here the scenario is basically like there are two cores and each core has 4 ROIs and in the input and also 4 ROIs in the output after a first operation. Here this output will become the input for next operation. For the next operation, it is also split in a similar way, so it will also need top and down borders. So these two ROIs marked in red on core 0 will need to share their bottom edge with these two ROIs marked in green. So they will become the top border for core 1. This also similarly, these two ROIs on core 1 will share their top edge with core 0 ROIs. Chimera Compute Library provides an API for sharing borders this way between cores. Graph compiler generates a call to that API with a number of borders to be passed, number of borders to be transferred passed as a parameter. This may not be always possible because, for example, we can also have next operation split on width. So just in that case, only sharing borders will not be sufficient. Also, there can be some shape transformation ops in neural networks, such as transpose, where sharing data this way won't be helpful. In those cases, we currently write the output back to external memory. Another challenge for multi-core systems is that when cores go out of sync, data can get corrupted, and this can result in wrong output. Here also we have a similar scenario, as mentioned before, where there are two operations executing one after another, but here we are taking the data out between two operations to external memory instead of sharing borders. So this in1 is first input for the first operation. It will be processed in array of processing elements. Then it will be output in this out tensor in L2 memory, and this tensor will be returned back to external memory. This process will happen on both cores. So when for example, if when reading the next operation, reading the input for the next operation, we will have we can have, for example, if we complete write out for out tensor on core 0 first and start reading into immediately before core 1 completes writing its output. In that case, we can read wrong borders, so that can result in wrong output. So we will need to put a barrier on these flows so that both the flows complete, both the write out flows complete first, and then we can go ahead with the next operation. So graph compiler has to identify this kind of scenarios where the write out will need a barrier on it, and there can also be some cases where it might not be required. For example, if the next operation is only element wise op, in that case we won't require any other data like borders. So in that case we can avoid this synchronization operation in between. There are like some possible extensions to this. For right now we have seen how we carry out splitting for convolution or element wise ops. They can get multi-core split currently, but we can also extend this to split other ops such as matrix multiplication, which are found in neural networks. Another thing is, as we get deeper in some neural networks, the input-output shape becomes very small. In those cases, sometimes it doesn't make sense to split the data on all available cores because it can result in low utilization. In those cases, we can instead use a condition on core ID to like only only execute those op on those specific cores. This will also save us some power because some cores will be inactive and other cores will be fully utilized. The way we are splitting currently is an example of data parallelism, where we are each core is working on the same layer of the network, but it can. This is because we at a time only one input is processed. But when we have batches of inputs, different cores can work on different parts of the network. For example, the first layer, for a subset of cores might be working on the last few layers for the first input, while the next for the next input, remaining cores will be working on different layer of the network. This is like just an overview for our SDK architecture. We can talk about this in detail tomorrow if anyone is curious.
Can you hear me? Yeah. Okay, so what Nilesh talked about is just this part of the compiler. We have the whole stack which we are currently working on. There are many interesting problems that we are working on, but because of shortage of time, we cannot discuss all of them. So if you guys are interested, please visit us tomorrow to discuss whichever part of the compiler you are interested in.
Thank you.
So we had, hi Samira, hi Nilesh. So we had similar workflow actually. So what are the challenges of not moving to MLIR? Do you see, because this is a solved problem, right? In MLIR it's more challenging that way.
For us, the challenge is simple. We are startup, we are small. We have started working on this 4 years back. So we cannot just, trash everything and start afresh, or we don't have parallel teams to work on it. If anyone is interested to join us, of course we can start working on that. So we have open positions on all the compiler fronts. So we want to move there, but currently we don't have resources to do that.
It's good to see somebody else in our board, similar board. Otherwise, everybody is CPU, GPU.
That's true. But yeah, for us, we want to go to MLIR, but it feels also nice, being a startup and still able to solve the problems which 3-4 years back, which people are solving now. So we have already solved those problems, so we are just making use of them right now. Any other question?
So my question is perhaps not just to Samira, but perhaps to someone, all people who are present here. So people talk a lot about MLIR, and I know MLIR is pretty good, but to the best of my knowledge, it's available only for Python inputs. You can't use it for its production infrastructure is not available for C and C++. People are still working on it, but this is what Uday Reddy told me 6 months ago. So does anyone know anything more about it?
MLIR is now in production for Fortran. The Flang compiler that's in the LLVM infrastructure fundamentally uses MLIR for its upper level translation to what is
from the Fortran AST?
From the Fortran AST to an IR representation known as FIR.
Okay.
Similarly, there are dialects for OpenMP and other things at that layer.
Okay.
So it is being used. MLIR is not just being used for ML as in machine learning.
Yeah, of course.
It is being used for something as ancient as Fortran.
Yeah. But I'm still waiting for C and C++. I just
It is in active development upstream for something known as CIR, which is going on at the moment, or known as Clang IR in the past.
That we had seen, we found many problems with it last year. I don't know what is the...
There is active development happening this year in the community among many people from the industry. So watch this space would be my answer for a year or two more, or however long it takes in open source to do it.
Thank you. Thank you.
Thank you for such an interesting talk. It was indeed interesting to know about graph compilers and the Chimera architecture of your company. I'm sure your talk has given some food for thought to all our compilers and architecture folk equally. I would like to request Professor Biswa to present Ms. Samira Deshpande and Mr. Nilesh Shirsagar with a token of gratitude. Thank you. Our next talk is by our eminent delegate from TCS Research. We have Mr. Ravindra Naik, who is a chief scientist at TCS Research, TRDDC Pune, with over 30 years of experience. He works with the larger objective of enabling the business transformation of TCS client enterprises by modeling and transforming their enterprise IT systems and re-architecting and refactoring their software applications. He has been exploring combining data and control flow analyses, formal methods for verification, code synthesis, machine learning, and Gen AI. Please welcome Mr. Ravindra Naik.
Hello. Yeah, thanks. So let me start my. Hi, good afternoon. So I think this talk is going to be very different from what we have heard in the earlier talks, right? I mean, most of the earlier talks were about compilers and the compiling technologies, optimizations. I'm going to switch the focus and speak a little bit about the future of enterprise IT systems. So, of course, this is driven by a lot of research work that TCS does in the space of software development lifecycle of enterprise IT systems. And so when I say SDLC, we work a lot on the software development techniques. We work a lot on verification and validation, and then all the phases of software development. And primarily, this is driven by the needs of TCS business, which essentially wants us to come up with potentially new solutions, new offerings that they can make to their customers. So those are the kinds of drivers. Of course, I am only mentioning a little bit about the software development space in TCS Research. It works a lot on process engineering. It works a lot on physical sciences. There is AI/ML group. There is group working on IoT, and there's a group working also on quantum computers as well. Mostly on the software side, except of course physical sciences, life sciences. Those are the two areas which work on real things, unlike us who work on virtual things. So I'm going to talk a little bit about this modernizing IT applications, and this is primarily driven by what we think, what is our perspective of the new IT systems. I'll talk a little bit about that in a short while. I'll probably show you one or two demos, and I'll talk a little bit about what role program analysis plays in the kind of problems that we are trying to solve, and see if some of you could be interested in some of the challenges that we are facing. Okay, so while he's onto it, okay. Okay, so this is just a picture of what the IT systems look like today. A very, very high level picture which says that there is some documentation, if it is there. Most of the real enterprise IT systems, may it be banking software or may it be insurance software or a retail software, most of the times we hear that there's no documentation available. But frankly, it's not true. Most of these enterprises do have some documents. Maybe it is functional document. It describes the insurance policies, for example. It describes the kinds of accounts that a bank offers to its customers. But there is some kind of functional documentation. There is some IT system level documentation as well. But when I say documentation, I'm really talking more of the domains, the business that the particular enterprise does. And on that front, we have always found that some documentation is there. How accurate it is, how obsolete it is, these are good questions. But yes, if it is a regulated enterprise or if it's a regulated business that the enterprise runs, then these documents are fairly up to date. So there is some documentation, and there is of course the IT system, because most enterprises today are operating in this, are automated, and therefore they definitely make use of IT systems. So what we see, of course, and this is slightly an older picture on the right-hand side. The top part is not older, where we see that enterprises are, especially with the advent of Gen AI, they want to make their documentation active, right? I mean, it has been a passive documentation. People write Word documents or fill in Excel sheets, but they want to make it active. And Gen AI is one way to make it active, right? They want their IT systems to be deployed on cloud. They want their IT systems to be split into business services. Unlike what you see on the left-hand side, you see a lot of boxes. So it's all still layers and boxes over there, but it is more on the technology front. The business operations themselves in many of the systems, or legacy systems, I would say, are still not servicified. They are largely monolithic, and we have seen this time and again, even today. That's a little unfortunate, but it is true. And in fact, by the way, TCS makes a lot of business in that space. But trying to move them to the new architecture, especially to cloud, and hopefully being able to split their monolithic system into business services. While this is what we want, hello. So while this is what we want, the reality is not that. For various reasons, may it be the cost involved, may it be the time involved. Many of the times, we take the old system and deploy it on cloud. I would be a little exaggerating over here. There are some business services that it created, but by and large, the monolithic nature of the application still stays. That's the unfortunate truth, and therefore, the reasons why enterprises want to move to these sort of new deployment architecture or new IT system, I would call, really are not met. Okay, there are some objectives that get met, but many of the crucial ones, especially making the system agile, making the system accommodate new features, new capabilities quickly, is indeed not met. What we think we want to do, nothing fancifully different, but what we think we want to do is not just take the documents and make them active, but basically extract the knowledge, the business knowledge from the documents, and capture that business knowledge in a repository form. So what you see on the right-hand side is our perspective of what the knowledge would look like. And I'll give a brief short demo to show you what I mean by vocabulary, by facts and rules, by products and processes. And basically, GenAI has enabled us to build the engines that this knowledge can be queried and can be exploited for various purposes, and we'll look at one or two of those purposes as well. Going forward, what value we are trying to add is two things. One is, how do we create this knowledge from documents? How do we create this knowledge from existing applications? And that's where source code analysis is going to play a major role. We'll again talk of some examples going forward. I'm just trying to give you the big picture here. Having created the knowledge, what do we do with it? So one of the things that we have attempted to do is to use this knowledge now for developing new software, to develop a new IT system. So rather than taking the old IT system and moving it to new, can we utilize this knowledge and extract the functional specifications and design specifications which form the input for building a new IT system? Again, we'll talk of that a little bit later. And these specifications then form a basis for building a new system. Now, what we see is, and this is just a start, enterprises are not interested in just creating the business services, but what they are interested is, can the decisions in the business services be made to the extent possible by the AI agents? So can the business services take some of the decisions? So for example, if it's a loan approval and there are multiple workflows, can some of these decisions be enabled by AI agents rather than by humans? And that is what they feel would add a lot of efficiency to their business processes. That is what would also reduce the costs that they incur in their processes. And these decisions are what we term, or what we believe, if we convert these business services into AI agents, and these AI agents exploit the data that is needed in order to make those decisions. So of course, the crucial part will be, how do I identify this data of making decisions by the agents? And that's, we believe, is another area where existing systems analysis, whether it is code analysis, whether it is dynamic analysis, is going to play a major role. So with this background, let me move ahead. I'm just going to quickly show you something that we extract from documents. I'm not focusing on source code here, but this hopefully will give you some idea of what we are intending to call as the business knowledge of the enterprise, and how do we extract it. So I hope this demo works over here, and you can hear the audio. No, I don't think it's working. Is there something that I've done to this adapter?
This is a demo video for
Yeah,
document
perfect, thanks.
digitization. This is the dashboard where documents are uploaded to the repository.
Let
This
me
is a
start it
demo
again.
video for document digitization. This is the dashboard where documents uploaded to the repository are listed. Now we add document EU rent a car. This document describes the car rental services and captures information about the. This is a demo video for
So,
document digitization.
somehow this is not coming up
This
here.
is the dashboard where documents uploaded to the repository are listed. Now we add document EU rent a car. This document describes the car rental services and
It's playing
captures
on mine, but it's
information
not
about
reaching.
their business rules. It
No,
includes
it's not
information
showing the
about
demo
rental
here.
and return time duration, steps to be followed before car allocation and at the time of handover, and conditions for a walk-in
It's
rental.
playing it on my machine,
Also
but
defines
it's
cases of no-show and late returns,
okay.
including
So I think I
incentives
just
under the loyalty program. Now we go ahead and process this document.
let me play it again. Sorry for that.
This is a demo video for document digitization.
Oh, the
This
screen
is
is
the
a problem.
dashboard where documents uploaded to the repository are listed. Now we add document EU rent a car. This document describes the car rental services and captures information about their business rules. It includes information about rental and return time duration, steps to be followed before car allocation and at the time of handover and conditions for a walk-in rental. Also defines cases of no-show and late returns, including incentives under the loyalty program. Now we go ahead and process this document.
No.
Since the document has been processed in the past, analysis files for it are already present in the repository, so we continue with them. After processing, we can look at the knowledge generated. This is a demo video for document digitization. This is the dashboard where documents uploaded to the repository are listed. Now we add document EU rent a car. This document describes the car rental services and captures information about their business rules. It includes information about rental and return time duration, steps to be followed before car allocation and at the time of handover and conditions for a walk-in rental. Also defines cases of no-show and late returns, including incentives under the loyalty program. Now we go ahead and process this document. Since the document has been processed in the past, analysis files for it are already present in the repository, so we continue with them. After processing, we can look at the knowledge generated. On the left you can see document hierarchy. We can have closer look at parts of the document using this representation, also depicts color-coded sentences. On the right you can see the knowledge generated in terms of sentences, vocabulary, and SBVR rules. The rules are represented in the SBVR notation, highlighting the terms and verb phrases. We can also see the dependency graph generated for the document, depicts relations where nodes are terms and edges are verb phrases. Looking at the document hierarchy, in terms of section, subsection, and sentences. Let's take a look at some sentence-specific knowledge. Here we select this sentence from the document hierarchy. We can see the processed sentence and the corresponding vocabulary. The vocabulary displays terms, binary facts, and n-ary facts extracted from the sentence. The SBVR rule specific to the sentence is also displayed, highlighting the terms and verb phrases. Now we take a close look at the graph. Here all the nodes of graph corresponding to the terms in the sentence get selected for better understanding of relations. The enterprise data generated includes vocabulary, facts, rules, and the document structure. They are stored separately as indexes, embeddings, hierarchy graphs and are used for different use cases as knowledge.
Okay, so I have to look at this and play with this. There's my arrow. Yeah, I think this is the challenges of technology that we have to face. So I think what I just tried to show you was what is it that we extract from documents, what is it that we capture, or what is it that we call as business knowledge of the enterprise. Okay, so this is primarily in terms or in words that that the enterprise talks about its business. Okay, not really about the software or the IT system. And that's where we'll see some challenges when we analyze source code or we want to extract it from the source code. Now, having extracted this knowledge, there are various things, use cases where this knowledge can be utilized. I'll probably just show you a very short demo of how what we do when we extract requirements and design specs, and why I think this knowledge is crucial. So again, probably I'll have to play a little bit.
This is the demo video of requirements and design model synthesis. This is the main dashboard displaying documents uploaded to repository. Let's begin by loading knowledge from a document called EU Rent a Car. This document will serve as the context for synthesizing requirements and design models. First, we will generate requirements. These requirements outline the fundamental needs that must be met for the successful implementation of the EU Rent system, defining its core purpose and operational boundaries. Here, the tool has generated 5 requirements as manage car rentals, maintain car fleet, customer management, pricing and discount management, and loyalty program management. Now let's focus on requirement 1, manage car rentals. To generate associated processes. Processes represent structured sequences of tasks that are performed to achieve specific objectives. Within the EU rent system, they represent the flow of operations necessary to fulfill the requirements. Here, the tool has identified 5 processes associated with managed car rentals, which are reservation process, car allocation process. Likewise, there are 3 more processes. Let's take first reservation process and break it down further into its constituent activities. Activities are individual tasks or actions that make up a process, each contributing a distinct step towards the completion of a process in EU rent system. For reservation process, the tool has generated 6 activities: receive reservation request, check customer eligibility. Likewise, there are 4 more activities. Now let's focus on activity receive reservation request to generate the rules. Rules are the specific guidelines that govern the execution of activities. They ensure that activities are performed consistently and in accordance with defined requirements. And processes. Here, the tool has generated 11 rules for activity receive reservation request, each categorized by a rule type and traced back to its source in the original document. Let's see few rules. Rule 1 states, most rentals are by advance reservation. The rental period and the car group are specified at the time of reservation. This is a business logic rule derived from section 2 of the document. Rule 3 introduces a capacity rule. Reservations may be accepted only up to the capacity of the pickup branch on pickup day. Rule 4 stating, if the customer requesting the rental has been blacklisted, the rental must be refused, can be considered as a compliance rule. Likewise, there are multiple more rules. This is the consolidated JSON file containing all the processes, activities and rules. Having established all the data, we move to next crucial step of generating design models for process. So for reservation process, we'll generate use case model, ER model, class model, and sequence diagram. The use case model visually represents.
So I think I'll kind of stop over here, stop this demo and go back to my slides. There is some more things over there. So what I just wanted to give you a glimpse of is what is this enterprise knowledge that we are capturing, and what is one potential use case that we have attempted to implement and share. And of course there are others that we have already worked on, providing help desk, copilot, and synthesizing specs for a platform from the same enterprise knowledge. Now, really, our challenge is this one. Now, documents, as we talked about, are obsolete and could be obsolete, and the real truth is really into the source code. So we need to analyze source code. We need to look at the source code and understand it, and figure out whether we can extract this business knowledge of the enterprise from the source code. And the whole idea is that can we close the gaps between what the document describes and what is implemented in the source code. Now, there could also be, the gaps could be either ways. One of them could be right, or maybe both of them could be right, and both of them have to be present finally as alternatives in the business. So this is the reason why it is crucial for us to even look at the source code as it's really the golden truth. Now, how do we do it? We look at standard code analysis. I think this is something that most of you are very, very familiar with. COBOL and C are our current targets, where we process it, where we parse the code, and we do run control flow and data flow analysis as a batch process. The only thing probably that is new over here is the domain annotations. So for crucial variables in the program, we expect descriptions of what it means in the domain. And what we do is we use data flow analysis, essentially building equivalent sets, to propagate these descriptions or annotations to the all other variables in the program. So that's one utilization of data flow analysis. But what really comes in is the on-demand analysis. So again, I'm sure you people are very familiar with this. But what this is essentially saying is that for a variable of interest, in this case we've just called it variable, it could be an event, it could be a state, what is the program slice that we can identify for this particular program And this slice, and I'll come to what this type of slice is, constitutes or it implements the business logic that we are interested in. So the business logic is for a certain variable, and then we use LLM-driven business rule extractor, which takes this IT rule, the domain dictionary, and synthesizes the business rules. So let me show you some quick examples. We kind of ran this on EU rent application. Again, this application also we picked up from the net. We kind of added a lot of functionality to it to ensure that we cover interprocedural analysis. And starting with the rental status, where the car rental has been successful, we essentially built a slice. You can look at all the slice points. Some places you would see that the whole function has become part of the slice. And what this slice is indeed an executable slice. So this is really the collated slice over here. This is an executable slice. In fact, this uses some of the work that Anushri is sitting here, she and her team implemented in terms of the C code analysis. And along with that, what we provide is what I called as domain dictionary. So for crucial variables, we gave some descriptions. And what we get using LLMs or using GenAI are business rules like these. Okay, I'm not going to get into the details as I'm running short of time, but I think the whole point I'm trying to make over here is that extracting business rules from source code, especially GenAI, has made it reasonably easy if we are able to partition the code properly. Now, of course, there are attempts to see if GenAI can do the code analysis itself. That's what some of the discussions today were focused around. But at least our experience as the GenAI stands today is that doesn't scale up at all. In fact, for real-life applications, and I'll show you something very quickly after this, it is at a complete loss in terms of extracting the slices that we are interested in. So partitioning the program into slicing, we still feel code analysis is going to be the prominent technique, and then combining it with GenAI can hopefully do the wonder or the magic for us. So let's look at one quick example of a real-life system. This is a steel manufacturing process solution, and I was just talking with somebody over tea. Even I was very surprised, by the way. This is a steel manufacturing company in Netherlands, which does its steel manufacturing. The steel manufacturing processes which are automated are written completely in COBOL, and they run on mainframe. Okay, so a complete surprise even for me. And if you look at some of the source code, I don't expect you to read it, but there is some variable. I can't even read it. Okay, so let me go back a little bit. So there is a variable. We did a POC, and they gave us some 9 programs containing something very concrete, or think of it as a module. And they wanted us to extract a set of 9 business rules triggered by 3 different variables of interest. So the variables of interest, one that I'm going to show you output is this I less mark WUK, which is related to marking of weld. So the weld has to be marked or not marked. And this exactly is what in this code is. So this is the place where the database is getting updated with I less mark WUKN, and actually that's the place in the top. In the same program, of course, where it is moving value j, and that j has some meaning. We'll come to see what that meaning is. Of course, our interprocedural analysis went across programs, and it figured out that not just the G300 program, but the G200 program also had assignments that move. So this is COBOL, not very different from C, but instead of saying simple equal to say A equal to B or A equal to 10, it will say move R to something. This is how COBOL is written. And there is, okay, you can't see the call over here. So G300 program makes a call to 200 program. And if you can see on the top, the move J to I less mark WKN is under certain conditions. And some of the variables in those conditions are getting set values over here. So simple data flow analysis, if you look at it, from the example point of view. But if you realize what we see over here, the collated slice, again, I think the way GenAI works, we had to try and bring in a executable slice, okay? Not just the data flow statements. So this could mean that we have to cover the controlling conditions, And in certain situations, we have to track the controlling conditions variables as well. So it's not a pure data slice. It's not a pure program slice. There is some combination of data flows and some combinations of control flow slice. And those are some of the challenges I'll try to list in the next slide. So along with the collated slice, what I'm showing you here is the kind of descriptions that the business team gave us for few of the variables, which we used data flow analysis to propagate in the program, and what we got is business rules of what you see on the right-hand side. So it does work pretty well. If you look at the business rule 1, it says that if the pickling line weld is not marked, the pickling line weld is coming from the variable functi ind not. Functi ind not, if you look, functi ind, sorry. So functi ind is essentially an indicator which talks about whether the pickling line weld must be marked or not. And depending on the value, it's able to figure out, GenAI is able to figure out what that condition means given just this description. So it's able to interpret, it's able to do some kind of interpretation, and this has been done using Llama 3.1, 7 billion model. So of course we have tried various different types of models, and in this particular case we had to kind of resort to local models because this is a customer code. So obviously we couldn't use GPT-4o or any of the models like Claude, which are essentially on the net. So yeah, I mean, those are some business restrictions we have to live with. So what I'm essentially trying to point out are some of the challenges. So we think these kinds of approaches where code analysis can play a very crucial role, and it may seem more like engineering than a core research, okay? But let me tell you, this engineering involves really some refinements in the core analysis algorithms as well. Not just from the precision versus scalability versus execution timeline, but also more from the pragmatic requirements of what I call as execution slice. I mean, I think that's some efforts that our team which worked on C code analysis. By the way, I think I must also mention that the analysis workbench that we have in Pune has its origins in IIT Bombay, long time, Professor Damderi's time, where we bought the work that Professor Damderi had done. And the analyzer generator is essentially primarily based on some of the work, very old work that IIT Bombay did. And it still works, by the way. So our code analyzer generator is common for imperative languages at least. So it works for C, it works for COBOL, it works for languages like PL1, RPG as well. Yes, it has some interesting difficulties with analyzing object-oriented languages, and that's why you wouldn't find C++ or Java over here. But I think the point I'm trying to make is that it's not just the precision versus scalabilities, but it's really the practicality of the code analysis that is at stake. And therefore, what we think is that it's not just the program slice or data slice, but what we are looking for is, can we come up with some kind of maybe a higher level language that lets us play around with different types of slices, that lets us play around with the context, the context that is the context for which business rule has to be extracted, which does not need to be just variables. It can even be the state. It can even be an event that is occurring. So we'll have to bring analysis of those concepts in place. So yeah, these are some of the challenges. I just wanted to mention it over here. If there's an interest, we could definitely discuss this further. So I'm not going to talk of the second problem over here. Just mention a passing remark that there is another area where we are working on. This is more for refactoring legacy monolithic architecture to microservice architecture. So the idea is that we wanted to take existing monolithic application and push it into a microservice-based cloud application, cloud deployed application. But I think the challenge always has been to identify the right microservices. And we think code analysis, it's not enough, but code analysis plays a major fundamental role over there. And we bring in the domain model or the domain knowledge as well in order to marry with this and use a GNN-based approach in order to do a clustering of all the nodes which represent the various elements in the code, with relations representing the structural relations which come from the code, and relations which represent domain semantics which come from the business domain. So I'll not get into the details of this, but this is another big area. What I want to just leave this talk is at this picture. This is similar picture, but what essentially we're trying to do is, we say that we want to extract business knowledge from source code as well as documents, and then once such a business knowledge is available, many use cases would start getting enabled, a few of which, probably just one of which I discussed or presented to you, but there are many such use cases that are possible with this kind of approach. It's not that that enterprises are moving to this kind of structure right away, but this is what we perceive is going to be the case. Thank you.
Do we have any questions?
Have you considered, have you considered integrating this with like CRM software? I think that's a very common use case of this, extracting requirements and, migrating to a newer CRM version or something like that.
Right. So, yes and no. The reason, yes, I'm saying is because, yes, there are requirements or there are needs expressed by the TCS team to move from, in fact, one of the projects that we are looking at, only for the business rule extraction part, is to move from COBOL to a CRM software. Okay. Now, the challenge with CRM softwares is that they are unlike typical COTS or commercial off-the-shelf platforms, which are purely configurable by parameter value pairs, and that's something that we can definitely generate from our knowledge. They have pre-built modules, pre-built functionalities. So the requirement there is to map not the business rules, but the functionalities from existing applications, the legacy applications, to the
those often have, I've seen like a lot of miscellaneous customization that needs to be done.
Correct.
Like, implement C# modules and JavaScript.
C# modules, if you look at SAP, SAP has a programming language called ABAP to do this configuration that you're talking about. So they don't, I mean, they do allow, of course, escapes to C# or to Java as well, but they primarily discourage it, because if they come up with a newer version, like for example, SAP S/4HANA is the newest version, they have removed ABAP and replaced it with new customizable programming language. So if you have programmed in ABAP, they will migrate you largely automatically. If you have escaped out into C# and Java, then it's your responsibility. So I mean, I think this is the way they run their businesses. They want to make money. So yeah, I mean, we have to live with it. So the answer to your question is partly yes, because most of these functionalities, they do have descriptions. And if they have descriptions, and I'm talking of functional descriptions, the processes and the products, then yes, extracting this knowledge, at least in order to create the definition of services from that knowledge, is feasible.
So I wanted to ask one question. Is the time?
Maybe we can take it. Yeah.
Okay, sure.
Okay.
Thank you so much, sir.
Thank you. Thank you.
It was indeed an interesting talk. It was good to hear that code analysis is still useful. I would like to request Professor Suprati to present our delegates with a token of gratitude. I would like to invite Mr. Pavan Kumar Chettimalli to the dais. Thank you. We have our next talk by our esteemed delegates from NVIDIA. We have Ms. Prachi Godbole, who works as a senior system software engineer at NVIDIA Pune. She has over a decade's experience in compiler development, middle-end and back-end, compiler optimization, GCC compilers, TVM compiler stack, an embedded system software toolchain. Please welcome Ms. Prachi Godbole. We have Mr. Girish Bharambe, who is a senior system software manager with GPU compilers at NVIDIA. He leads the PTX compiler and assembler-disassembler tools team, contributing to CUDA and PTX since the Fermi generation. With expertise in GPU programming languages, linkers, and ABIs, he holds multiple patents in GPU abstractions and runtime. Please welcome Mr. Girish Bharambe.
Am I audible? Yeah. Okay. So, hi everyone. I know I'm standing between you and lunch, so I'll hopefully make it worthwhile for your wait. So what I wanted to talk today is about three things. Briefly, what we do at NVIDIA with respect to compilers. And then we are going to talk about two problems which are interesting and how we are trying to solve them through compiler technology, right? So last year when we were at Placid, we kind of showed how NVIDIA has a technology stack which is very heavy on the compilations side. And this is kind of summarizing all the compiler stacks that we work on. So we work on LLVM, GCC, OpenJDK, MLIR, XLA, and we have our own proprietary compilers as well. And through this, we are powering many of the technologies like Vulkan, DirectX, CUDA, PTX, OpenCL, and so on. So if you look at it, what we are doing is we are very broad in terms of the compilers that we work on, including open source compilers and proprietary compilers, wherever it makes sense. So there are cases where we work in the upstream, and there are cases where we work on the proprietary things. And through this, we are trying to power as much technology as possible, which is really relevant for any computational problems. Okay, so if you look at deep learning software stack, right, it's kind of getting very much complicated. It's layers of various things which are sitting on top of each other. So we have at very high level things like PyTorch, TensorRT, JAX, which are used for programming some of these machine learning frameworks. Then under the hood, we have CUDNA and cuBLAS, which are NVIDIA libraries which are helping accelerate some of the operations for these. And then we have some of the custom DSLs, so-called, which is Cutlass, Triton from OpenAI. And these build on foundation layers of CUDA, C++, NVVM, and PTX. So if you look at this whole DL stack, right, it's kind of various layers. And the most interesting, and one of the interesting things about this is, all of these actually have compilers in them. So when I say compilers, it's not just at this below layer, which is traditional compiler of CUDA, C++, NVVM, or PTX. Each of this, starting with TensorRT, actually has a compiler in it. And the reason why we are seeing so much of the compilers usage is because fundamentally, DL is bottlenecked on optimizations. And optimization is a domain-specific problem. So if you want to solve optimization problem, you have to do it at different layers. Because at each layer, the amount of information you have is different. And by the time you get to a lower level, you may not be able to do any kind of optimizations which otherwise are possible in layers which are at TensorRT. At the same time, you can't do all those optimization at TensorRT layer itself, which is why each of this layer, for a variety of reasons, has compilation-based technology in it, and they try to solve problems with the information that's visible at that layer. So in nutshell, what is happening at NVIDIA is there is a lot of compiler work which is spanning across the entire stack. The kind of compiler work happens, like for example, TensorRT has a graph compiler in it. Whereas if you get to CUDA, C++, and NVVM, it's more traditional compiler. So we are kind of intersecting all these compilation technologies together to form this vertical stack, okay? And what I want to do today is talk about two problems. The first problem I want to talk about is Tensor Core abstractions, okay? And then Prachi will talk about something which is on the CPU side of things for call clustering. So what is Tensor Core? So for those who are familiar with NVIDIA GPUs may know there is a unit called as Tensor Core. But basically what Tensor Core is doing is it's doing an operation called as matrix multiply and accumulate. So it is doing A into B plus C. Okay, so you have A matrix, B matrix, and C matrix, and you are doing A into B plus C. Now this is very fundamental operation for implementing any of the gem kernels, which is one of the fundamental building blocks in all of the deep learning stack. Because of this, there is a dedicated hardware, and the way things work in the NVIDIA GPU for these tensor cores is this is a collective operation. That means multiple threads will cooperate with each other to perform a m by n by k tensor core operation. Okay, and each of the thread will have a slice of the matrix data which it will operate on to compute the overall thing. Okay, now if you look at how things have evolved for tensor cores at an NVIDIA GPU, it is very interesting, because when we started off with tensor cores in Volta GPU, we had an implementation in hardware where 8 threads were cooperating with each other to form the tensor core operation. In Turing and Ampere generation, we had 32 threads which were doing it. In Hopper generation, we had 4 warps, which is basically 128 threads which were doing it. And in Blackwell, we are going much wider, where we have 2 thread blocks which are actually cooperating with each other to form the matrix multiply operation. Now, what happens because of this is, if you look at the underlying machine and the architecture that is present, it is fundamentally shifting the granularity at which the operation happens, right? And the granularity changing, what I have shown in this diagram is just the thread level granularity, based like which threads are participating. But if you actually study things in bit more detail, you will also see that the storage format is also changing based on which generation of the hardware you are working on. Where the matrix is actually stored is also changing. For example, in Volta Turing Ampere, the threads were operating on registers. So the matrix data had to be brought in registers and was operated on registers. In Hopper, we had capability of doing it in shared memory. And in Blackwell, we have a new memory called Tensor memory where things happen. So both the storage of the matrix is changing, and the threads which are participating to perform this operation is changing. Now the problem is, how do you build a machine which can give this functionality in an abstract way? Because your underlying architecture is changing in a very drastic way. So there are 3 problems with respect to programming tensor cores. One is portability of tensor cores, because as I'm showing you, the difference from one architecture to other architecture is just too crazy to be able to model in any sort of compilation layer. So portability of the applications is affected because your hardware is changing drastically. Second is, for a variety of reasons, the programming interface for tensor cores has to be through Python, because many of these higher level frameworks are based in Python. And third is, since we are a GPU company and we need to give the best performance, whatever abstractions you are building have to be performant. You can't sacrifice even 1% of the performance for your abstraction. So these are the 3 problems that we wanted to somehow solve with tensor cores. So just a brief background on how GPU runs the kernel and why this problem happens. So typical way of GPU programming is you have some array of data, right, which you want to process. You break it down into set of blocks, right? So you divide your problem into small chunk, and you further divide each of this block into set of threads which basically operate together, right? So this is the classic hierarchy of CUDA, where you have a grid, you divide it into blocks, and each block is divided into set of threads, right? And all of this mapping is done by the application, right? Where once the application is there, it will decide which thread item will compute which part of the data. And this is basically the thread level parallelism model that NVIDIA GPUs provide. And this is where the problem actually starts for tensor core. Because as I said, tensor cores, our underlying hardware is changing based on how many threads are cooperating with each other. Now, as soon as you break down your problem to a level where threads and data mapping is fixed, your program becomes non-portable, because same program will not want to work on the next generation hardware where we are changing that mapping. So what do? Let's take a step back, right? So instead of going all the way till thread level parallelism, can we take a step back and say that once the data is divided into set of blocks, all of this data, if you look, is actually slightly more regular, because each of this would be a tensor, each of this would be some sort of matrix or some array kind of data. And this is where we are actually able to also map it to our GPU. And this might be a much more simpler program as well. Because as a program, what you're simply doing is you're dividing your original data into set of blocks and then leaving that to the compiler. Okay? So that's the basic idea of what we are trying to do with Tensor cores. So if you look at it, we have 3 hierarchies of execution models. One is grid level parallelism, right? Which is where you have your entire data and you just give it to a runtime system and say execute this and give me the data back. This is typically the model that PyTorch and other frameworks provide, where your entire data is given to the runtime. The entire runtime and compiler will be responsible for dividing your data onto the execution cores. And then we have this block level models, which is what I'll talk a bit more about, where as an application, you will break your problem into the block level, but leave it to compiler and runtime to map it to the actual threads. And then we have thread level thing where application is responsible for doing the end-to-end thing, right? So these are the 3 execution models which are present. I want to talk a bit about this block level thing and something new that we are adding with CUDA. So we are adding something called a CU tile, which is a tile-based programming in CUDA. So what this will do is this will allow people to represent their operations as tile data. Okay, so as a programmer, you would divide your program into set of arrays or set of tensors, and then you could perform operations which are tile based, which is basically A plus B equal to C. So as a programmer, you don't have to write which thread is doing what. You will simply say that I want to perform an operation A plus B equal to C at a tile level, and compiler sitting below it would be responsible for figuring out how things actually go. And so basically, if you look at this at a program level, the abstraction is much higher than what it used to be for CUDA. And the compiler would be essentially responsible for doing the SIMT level mapping of that, right? And what we are doing for tile-based programming is, this is not yet added. It's something which is work in progress at NVIDIA. We are hoping to release this later this year for CUDA Python. So first we will release the Python-based support for this, and then we'll release the C++-based support for this. Now, the good part about this tile-based abstraction is it can also hide away the complexity of the tensor cores. Because now what you can do is, in your program, you can represent your operation more like A into B equal to C or A into B plus C, and you don't have to divide it to individual thread and individual data element layer. And the runtime sitting below it will actually be responsible for mapping it to the appropriate generation of the tensor cores. Okay? And this basically will allow programs to become portable across NVIDIA generations. You may still have to actually retune your application for getting the maximum performance, but this will provide the portability that otherwise was very hard to achieve with the tensor cores. Now, what we are doing is we are introducing something called as tile IR, which is a new IR that NVIDIA will provide. And if you look at this stack, it looks very interesting because now we have all these frameworks, TensorRT, CUDN, and kublas, and they would call into, for example, CUDA C++ for any operations that they want to do for traditional SIMT style execution. But they now also have a path through CU tile to target tile IR, which would represent things natively with respect to the tiled execution. Okay? So tile IR would form a representation which is parallel to PTX and parallel to NVVM, which allows you to express the tiled-based computation. So for any programming, and this is not just for DL. I mean, DL is probably the application which is going to make heavy use of it, but this is a general purpose extension to CUDA and can be used anywhere in terms of, so there are a lot of HPC applications also where you might be able to represent your computations as tile-based computation instead of SIMT-based computations. And that's where you can actually target tile IR, okay? And since it's a compiler-based target, one of the good things is we will allow people to target tile IR, so you can target tile IR from your DSLs. So just like currently NVIDIA allows NVVM IR to be targeted for any SIMT programs, you will be able to write programs which can translate directly to tile from your higher level language. For example, we expect eventually OpenAI Triton to also map to tile, in which case all of those paths that currently have to go through the PTX SIMT path can directly go through the tile path and get benefit of it, right? And what we are doing is all of these can coexist together, right? So the beauty of this is both of these paths can coexist. So your application can mix use of SIMT and tile together, and your final binary that you will produce can have both of them mixed together. Initially, we expect the mixing to happen at a kernel level boundary. That means you cannot have a single kernel that will have both tile and SIMT codes. But eventually, we plan to relax that as well. And that's where there are a lot of open challenges on how do you mix these two programming models in a single function. And that is something that we are planning to work on. It's not something which we think we have solved yet, but it is something that we need to solve. As of now, we are taking a slightly simpler path where we are saying that your kernel can either be tile-based kernel or a SIMT-based kernel. And you can call from one to other, but you cannot intermix them together, okay? So that is one of the areas where we'll be looking at. And just to give a glimpse of why it is a harder problem is because when you have tiled-based execution, you need to ensure data is accessible in a particular way for Tensor. Whereas when you bring it back into the SIMT, there are complexities on how the thread level mapping needs to happen. And if you go back and forth, how do you do that efficiently? So what sort of ABI needs to exist between these two programming paradigms to be able to make it efficient is an open-ended question, right? So that's all I wanted to talk about in terms of tile IR. I'll hand over to Prachi, who will talk about a slightly different problem, which is related to CPU compilations.
Use this. Thanks, Girish. So next, I am going to focus on an entirely new problem and at an entirely new end of the spectrum. So the optimization is called call clustering optimization. Code locality optimizations and their related problems are not new. There are solutions, those work, but the modern applications, large and especially heterogeneous applications, introduce new challenges, especially today's applications with deep call chains in their hot paths. They represent wide range of applications we are seeing today. They contribute to this locality problem a lot. I have an illustrative example here. We have a large application, and as you can see, the entire call chain is so spread out over the virtual address space that this is a very bad code locality. And we have observed that such spatially sparse functions actually bottleneck the overall performance of your system or your application. Now we are trying to solve this in the CPU and in the traditional compiler, GCC compiler for our CPU. The core idea of the optimization is to cluster together entire call chains and put them together locally so they are co-located. But the problem is not so simple. Because the applications are so large and probably millions of functions at a time, and the call chains themselves are very complicated, you require a lot of information to provide to the compiler to even begin solving this problem. So this has presented, as I said, new problems. So far, we have solved it partially. This is a very ongoing activity at the moment. This is no way solved completely. But in its current format, we have inter-procedural analysis pass in GCC, which essentially works at LTO time, which is link time optimization, because these sort of large applications do require a lot of runtime feedback and whole program analysis. So currently our initial feature support is upstream for review. Through this optimization, I not only want to discuss some of the details of the optimization, but also focus more on the infrastructure or the very tool chain infrastructure, as well as the compute system challenges that we see and have to solve in order to solve the problem. So at the bottom here, we have a code, sample code, which is heterogeneous code. And these types of codes are representative of this problem, even more so than the CPU-only applications. And if you see, both CPU, GPU, and other compute systems are involved in this application. So any bottlenecking on the CPU side via code locality is going to result in overall loss of performance, which is not acceptable. So starting from this troublesome application, the first step into the solving of the problem is to gather profile information. Profile information and PGO related optimizations themselves are new. Their incorporation into customers' compilation flow is new. And there are challenges due to profile quality as well. So before we even begin solving the problem in the compiler, there are issues with deployment of the profile guided optimizations or deployment of the about the quality of the said profile and so on. So in this picture, profile information is one of the inputs to the compiler pass, as well as our input LTO objects. As I said, this optimization, because the applications are so large, LTO is the first time where majority of the code comes to the purview of the compiler. Before that, you have separate translation units, and LTO is the first time where you have almost all of the code, and therefore this has to be an LTO pass. Here is a simple structure. This is obviously very simplified, but this is the simple structure of the pass. The pass has to operate on the global call graph. And the pass itself is divided into two phases. First is called clustering or reordering. Now, traditionally, in the hot-cold partitioning scenario, you would just divide your functions into hot functions and cold functions, and then lay them out one by one. Now, in these large applications, because the hot part of the code is so large, it's not sufficient to just call out the hot functions and cold functions, but you have to go one level deeper and affine your callers and callees to their particularly especially hot callers or callees, and then do the reordering. So the first pass deals with this reordering, and the second phase is something called as function cloning, where you have an option to affine one callee to more than one callers to increase furthermore locality. And then hopefully we get a good performant application out of it. This picture just depicts what the first call clustering is trying to do. It is trying to partition your call graph into different partitions. And you see that the I3 node over there is in partition 1, but there is a call from I2 to it, which is in partition 20. So in the next pass, you have the option of cloning that particular node. Now there are certain heuristics which are under development to help this out further, and those include C++ features, any language features, for example, templated code. We are trying to see if we can make use of language features to draw out extra characteristics of from the application and make use of that, and other static heuristics. As I said, there are challenges throughout the entire stack and entire tool chain for this optimization. I have just called out a few of them. I'm not going to go into details, but we can discuss this more later or tomorrow. I would just like to conclude with our message here. So you would have seen by now that we have at NVIDIA, we have such diverse compilers and a deep stack of compilers. Each of them are trying to solve problems at different level. But the key message here is that compilers have always played and will always continue to play an important role. Yes. And new programming paradigms, new programming abstractions are getting traction, and compiler is there to serve that. We've talked about hardware, software co-design, and I think both optimizations illustrate that beautifully. And yeah, so I would like to see all of you in the breakout sessions to discuss these two problems. I think you would have got additional problems from us, so feel free to join us in our breakout session and discuss with us. Thank you.
Any questions?
Yeah, this is not really a question, more of an observation. So call cluster optimization, I would say, is a real classic problem to solve. More importantly, it's a problem that we created because if you look at the modern programming abstractions, more importantly, the object-oriented design, we combine the code and data together because that's how the programmers see it. But the machine see it differently. They want the call chain and the associated data to be put together, which is always a conflict between the programmer and the system. And that's where the compilers can play a huge role. More importantly, to see how the models can be different, which is more aligned to the machine than to the programmer, still providing a good experience to the programmer. So it's a very good problem to solve. I think escape analysis has been doing some part of it, but it's having limited scope. There are a lot of work to be done on that front. Thank you.
Thank you.
I have a question. So my question is on the tile IR. So I'd like to ask, like, what is the guiding principle of this IR? I saw a slide where you were translating some Python code into tile IR. So the main question here is languages like Python, JavaScript are adding support for these high-level features like generators. Sometimes the environments are first class, and there are a lot of these dynamic sort of systems at play. So does the IR try to model all these high-level abstractions, like maybe even lazy code execution? Maybe you could memorize some certain functions because they are pure.
No. So tile IR is not meant for these kind of execution environment-oriented aspects. It is more about how do you represent computation, which otherwise is very hard to represent or is non-portable to represent when you break it down to thread-level granularity. So think of fundamental computations that you are doing today, which might be, like, for example, softmax. That would be an operation that would be natively represented in tile IR because it forms a block level operation and makes sense to have a native representation in tile IR because that way we could lower it into the most appropriate way when it comes to underlying hardware, right? So we are still looking more from the computation point of view in terms of what computations are block level computations versus thread level computation, and whatever forms a block level computation algorithmically is what will find its place in tile IR.
Okay, thank you. Yeah, so I will make it quick. My question is related to the second part of the talk. So you said about large applications. Could you spell out the code footprint? Like it's in MBs, tens of MBs, or hundreds of MBs?
So most of the AI applications today.
No, but the code footprint, not the data.
Okay.
It's fine if you are not allowed to say. But at least if you have a range, then that will be helpful.
Yeah.
Hundreds of MBs?
Yes.
Okay.
Yes.
We're talking about those sizes. They are working in large frameworks, and the dependency in the libraries and that comes from the Python ecosystem and so on.
So if you look at the first diagram that I was showing, which is basically layers of stack, that is what is basically adding into these, because every layer is handing off some work to the next layer, to the next layer, to the next layer, which kind of ends up forming this call chain. And then you have these locality issues that start happening.
Yeah, I have a follow-up point. So Intel and ARM recently they have started supporting profile guided function prefetching. So the ideas like iSpy and all. So whether your ideas will be in synergy with those kind of ideas which are already there, any thoughts?
So surface level might be, if they are more related to data, then this is trying to solve a different problem.
No, it's on code. It's on code.
Yeah.
It's
Yes.
code. Yeah, the control flow jumps.
Yes.
Yeah.
Yes.
Okay.
Definitely.
Yeah, thanks.
So the CPU we have targeted is the gray CPU, which is an AR64 implementation. So a lot of the things that we do is fundamentally in those sort of parameters. The hardware features being used for profile guided optimizations would be in the form of industry standards that are already there in the AR64 ISA, or the architecture, I should say. And there may be additional things that we do ourselves. This is going to be a marathon, not a sprint.
Hey, related question. Sorry, just a quick follow-up to the same question. What's the performance upside we are talking about? Is it the 10 to 20%, or is it like 2x, 3x kind of performance enhancement?
The more the merrier. But no, I think somewhere upwards of 10-20%, if we are able to get, that's still a huge benefit. And what we are more interested in as a research project is some of the static heuristics, which in the absence of profile guided optimizations, to see where we end up with.
Again, related and as well as a quick question. So, does the bottleneck come because you try to load all the functions, the whole code of the functions, or so for example, JITs use trace-based compilation, right? They compile a trace and the hot paths are all clubbed together. You don't have all the code. Will it help?
It would help in a traditional CPU dynamic linker design. We don't have such leverage, but yes, it will help, but there are other sorts of deployment problem in that solution. So we have not only looked at the problem from compiler point of view, but the entire stack, compiler, post-binary operations, or link time or load time.
There is no common IR across these, right?
Unfortunately, no.
Okay, that would be one solution, but
yes.
too long.
Thank you. It was a very interesting talk, and we loved how the talk was summarized. So we have more delegates from NVIDIA. I would like to call Mr. Ramana Radhakrishnan, Mr. Malay Sanghi, and Mr. Shekhar Divekar to the dais. I would like to request Professor Biswa to present a token of gratitude to all the delegates from NVIDIA. First, Mr. Girish Bharambe. Ms. Prachi Godbole. Mr. Ramana Radhakrishnan. Mr. Malay Sanghi. And Mr. Shekhar Devekar. Thank you very much. And finally, after some exhilarating talks and conversations, it's time to take a break. Lunch has been arranged on the first floor of the adjoining building. We'll have our volunteers in the yellow tags standing outside to guide you, to show you the way. All the student attendees are requested to show their Placid IDs at the lunch counter. And do enjoy your conversations over lunch, relax, rejuvenate, and come back latest by 2:25.
इसको डायरेक्ट बस ये ना डायरेक्ट है
तो डायरेक्ट अभी इसको निकालने का नहीं। हाँ मैंने देखा।
Welcome back, everyone. We know you've just had a scrumptious meal and might find it difficult to attend talks. So fret not, we've got your back. Interesting conversations ensue when great minds come together. And wouldn't we love to see our delegates together on the stage for some enriching and interesting insights? I would like to invite our panelists one by one. Our first panelist is Mr. Ramana Radhakrishnan, who is a seasoned compiler expert with over 2 decades of experience. A key contributor to the GNU toolchain, he has worked on CPU architectures like AArch64 and serves on the GCC steering committee. He currently leads the OSS CPU compilers team for NVIDIA's Grace Data Center CPU and has contributed significantly to the GCC build of ARM and LLVM. Please welcome Mr. Ramana Radhakrishnan. Our second panelist is Dr. Abhijat Vichare, who is a renowned figure in computing and education. He has made significant contributions to GCC internals at IIT Bombay and system software projects using GNU tools. A former scientist at CRL Pune, he has also played a key role in shaping computing education, including serving on the ACM IEEE Computing Curricula Steering Committee. Please welcome Dr. Abhijat Vichare. Our third panelist is Dr. Aseem Rastogi, who is a senior principal researcher at Microsoft Research India. His work spans the areas of language design, type systems, program verification, and software security. Most recently, he has been exploring the combination of large language models, LLMs, and symbolic tools to improve software security and reliability. Please welcome Dr. Aseem Rastogi. Our last panelist is Professor Saurav Bansal, who is a professor at the CSE department at IIT Delhi. He currently works at the intersection of formal methods, compiler designs, and AI algorithms. He is currently working at Graviton Research. He was also involved in a startup that aims to commercialize the end-to-end translation validator developed as a part of the research done in his group at IIT Delhi. Please welcome Professor Saurav Bansal. The panel discussion will be moderated by Professor Uday Khedkar.
So, very warm good afternoon to all of you. One privilege of being a panel moderator is one mic stays with you, whereas two other mics float around in the 4 people. So what we are going to do here is we have a very simple model of panel discussion. I'm going to ask them some questions and I will call out their names in some random order. I will want all of them to answer this question, maybe an answer in about 2-3 minutes per question. Then, depending upon the time, we will open up the same questions to other delegates from the industry. And we might even take some questions from the audience, maybe from online audience, because Manas has done some homework on the questions that have come. The goal of this panel discussion is to bring out some original thinking, some of their own viewpoints. As I said in the beginning, the idea is to help people find their own coordinates. And the best way of helping people find their own coordinates is to ask people, how did they find their coordinates? And then we can decide whether those ideas help us or not. The second privilege of being a coordinator of a panel discussion, moderator of a panel discussion, is that I get to answer the questions, but I don't have to answer any questions. So that's a big privilege which I'm going to use. So my first question, and I'll take the names of the panelists whom I'll ask. So my first question is, how and when did you get infected by this virus called PLN compilers? So let's hear from Aseem maybe. Aseem, you want to begin?
So I think it was just by chance. When I applied to grad school, my application was in networking because I had spent some time at Tejas Networks as a software developer, and I saw some real world problems, and that's what I thought I'll solve in the grad school. So my application was in networking. I went to grad school. I met the professor who had promised me summer funding. He was a networking, he still is a networking professor, it was Himanshu Gupta. When I was talking to him, he kind of implored me that, why are you so tied to networking? Grad school is like a new start, so why don't you explore other fields and see what other areas are there and then figure out what you want to do. So I said, okay. I mean, at that time I felt a little sad that he was kind of pushing me away, but in hindsight it was a blessing. So then in my second semester I took the grad school, the grad course on programming languages, Professor C.R. Ramakrishnan was teaching it, and he introduced us to this types and programming languages. I don't know if people have heard of that book. It's by Benjamin Pierce. And I think that book just did it. I was like, this is beautiful. The type system judgments, the operational semantics, the way you prove things about them, and the kind of things that types can encode, like abstraction, compositionality, modularity. I was just sold. I was like, this is it. This is what I want to do. So that's where I started. Then I changed grad school. I went to I did my master's from Stony Brook, but then moved to University of Maryland in College Park, where I worked with Professor Mike Hicks. My thesis was in new programming language for secure multi-party computation. It's a crypto protocol. And then after that, family constraints, I had to come to India, but I joined Microsoft Research, where for about 9 years, I worked on mathematically proving properties of software that we write. And now recently, I've been exploring static analysis and large language models.
Thank you, Asim.
Thank you.
Saurabh?
Hello. Hello, thanks. Thanks, Professor Uday, for having me here, allowing me to attend this and also being on the panel. So I, when I was an undergraduate student at IIT Delhi, I started looking at theory. Then I also did a little bit of networks. Then I joined a job at IBM Research where I was doing all kinds of things, but networks and a little bit of databases. But I realized that I wanted to go deeper into the software stack. I wanted to understand like the OS level things and so on. Then I went to grad school at Stanford University, and where I did courses in operating systems, both and especially the advanced course where I read a lot of papers on operating systems. And I also did the compilers course. And so I liked the ideas, and I realized that compilers actually playing up in multiple places, and it had some very cool things and it was very impactful and also very theoretically beautiful. So that struck me, and then I was looking for advisors for my PhD. Then I was looking at both compilers and OS, but then my advisor, Professor Alex Aiken, proposed this problem of super optimization to me, which I found most interesting. And so that was my journey into compilers. And yeah.
Thank you, Saurabh. Abhijat?
Well, I mean, I was intrigued by this problem since a long time. I don't know. I mean, I have been a physicist, so we have written programs in Fortran, which not many people probably would know. But the idea that you could express something and the machine would exactly do it like that was very interesting. And those questions were there. But being a physicist, well, if it's a tool, you use it to prove your physics and get your physics right. But then fate had me go into computer science, and at that point, whatever questions were there, PUCSD, Pune University CS department was around, Uday Khedkar was around, and he hopefully has forgotten all the questions I've asked him and troubled him at various points, in canteen or in classrooms, wherever. So those questions were there. And then I had this opportunity to come over here at IIT Bombay and look at GCC internals. And that's probably the time when I say I would become a PL guy. Oh no, yeah, before that, I learned Scheme. Now that really got me thinking. I mean, closures, continuations, God, okay, that is quite crazy. I never really thought of control flow and those kinds of things that way. But when I came to GCC and I really saw how things work, that was the point when the education part in me really came up, and I said, okay, we probably need to have a control structures course along with a data structures course. But that was the point when I would say that yes, at IIT Bombay, I really went into programming languages, and the bug caught me there. It still is there.
Ramana?
I would say sometime in the year 2000 or 2001 was when I caught the bug of systems programming and moved into compilers. I did my master's in PUCSD. Dr. Khedkar was my prof for many subjects there, including compilers, and playing around with low-level software at that point, writing assembler, and absolutely hating it, but still doing okay with it, meant that I liked the idea of writing compilers more than anything. I was also intrigued by data warehousing and data mining at that point in time. Those were also quite hot. So did 2 electives in them as well at the same point in time as doing a compilers course. I think ultimately compilers won. What really swung it for me was going into a startup with one of my classmates from Pune University and having no one to tell us anything about compilers. So we had fun and we made all the mistakes we could do. That still kept me there. So yeah, that's really, I would say, second semester PUCSD was where it started.
Thank you, Ramana. So I can take this opportunity to share with the audience that Abhijat, Ramana, and Samira is sitting there. These three people have been my partners in crime for a very long time. They are the ones who, Abhijat and Samira helped me set up the GCC Resource Center, and Ramana helped us to design the GCC workshops that we conducted from 2007 to 2010. And even now I bump into people who say I shifted in the area of compilers because at GCC workshop. I can say there are at least 2 people sitting here from GCC workshops, someone from 2007 and someone from 2010, yeah? Biswa, which year did you attend it? 2010. Thankfully, he didn't convert to compilers. Yeah? 2007. So these 3 people are the people who have helped me a lot to discover GCC internals. So coming back to next question, the next question is very simple. If you got infected with this virus, what did you do not to get rid of that infection? What kept you excited about this work that you do? Maybe Saurav?
Sorry. So yeah, I think when I started, it was more about just the love for doing low-level systems work and kind of enjoying that. But as I kind of worked more and became more, I started appreciating the fundamentalness of this area. Basically, the way I see it is that humans have to express logic in some language, and that has to be something that is intuitive to a human. And then machines have to understand logic in some other language, which has to be efficient for the machine to execute. And it is pretty clear that the 2 are completely different in how they should look in an ideal world, because a machine is billions of transistors and a human is sequential thinking. And so to me, that is a very fundamental bridge that needs to be crossed, and I think we have only crossed like a small portion of it. So it seems like it's a huge thing. There's a huge headroom to improve. And that's why, that keeps me excited about it.
So, Abhijat, maybe what keeps you excited about this area?
Many things. In fact, one of the things that Saurav just mentioned, the very core nature of this field. But when I am sort of writing an assembler or a compiler or interpreter, whatever it is, one of the things that always captures my attention is the conjunctive nature of the algorithms that I have to really work with. They have to work for all inputs. And trying to rack my head over is like, okay, will this, whatever I'm implementing, take care of that? That is something that keeps me very much focused on that. No, focused on the question, and at times I actually lose the project also. So that's one thing that happens. And then of course, once the daydreaming starts, I go on to try to think about various aspects of this world, what is abstraction and so on and so forth. But yes, that's what keeps me going.
Asim?
So for me, it's maybe two things. One is the love of programming. So I just love to program, and programming languages allows you to learn about, play with different kinds of abstractions, types, and so on. So that's one thing. The other thing is to work on problems which are both theoretical but also have a practical impact. Like I don't think I'll be happy working on something that's pure theory. So at least I've been privileged to have gotten into problems even when I was working on the proofs. I mean, it's very mathematical. We are doing mathematical proofs of the program, but then we were eventually bringing those to real software, and we were building piece of proven code which are deployed in the real systems. So I think that mixture of theoretical aspects of programming languages, just how nice things are in theory, but also making impact on real systems. I think that has been the key to me to, make me wake up every morning and go to work.
Ramana?
What keeps me excited even today about compilers? The thing fundamentally for me is, as I said, the thing that excited me about getting into compilers was generating assembler or generating low-level code. Now the amount of compute and the different styles in which computer architects, if there are any in this room, I'd like to apologize. But the number of funnies that they create without thinking about how software would deploy it is a lot of fun. That lends itself to figuring out solutions to really, really hard problems. And that keeps me excited. As an engineer, if you ask me today, what is it that excites me? Removing 5 instructions or finding out a more efficient sequence of instructions for a particular input that makes the entire application go faster, that's what excites me. If you ask me as somebody who worried about security, does it make it more secure? Then yeah, that makes me excited. So it's figuring out that metric and deriving the enjoyment from the translation is what excites me about compilers and continues to do so.
Okay, so thank you very much. Let's come to the next question that I had noted down. So can you mention some of the recent advances in the area or in the work that you are doing, not necessarily general compilers area, but whatever you are doing, that you consider very significant? When I say recent, as in maybe in past 5 years or 6-7 years. So maybe Asim, want to begin?
Good to have the first opportunity. So I'm just going to mention large language models here. So now others have to figure out something new to say. But in all seriousness, I think 2 years back when large language models happened, I think at least me and folks in my group, we saw it as an opportunity to say, hey, we have been working on improving software quality for some time now. And can this be another tool in our toolbox to scale the techniques that we have been working on and deploy them for real, on real software at scale? So, which is why I think 2 years back we have this group in Microsoft Research where we work on future of scalable software engineering, where the goal is to basically modernize, make real software better with the help of large language models. And we are not leaving behind the formal tools, the formal techniques that we had, but more like we have these large language models, what can we build around them to be able to solve the same problems at scale with high quality? So that I would say has been I think a shift for me in the last couple of years.
Thank you, Asim. Ramana?
So to me, it's been, at least in terms of development, it's been the explosion of new languages, new programming models that is coming at the input stage to the field of compilers. And the other side is the power of compute we now have at our disposal. These are two, this lends itself to thinking about engineering solutions that we couldn't have dreamt about in the past. Now those solutions could be built on generative AI, They could be closer to home. We're trying to deploy whole program optimizations. I don't know if any of you know, or I hope most of the Linux distributions that you have running on your machines are now compiled with link time optimizations. So that wasn't possible 10 to 15 years ago. It's now possible. It's happening. The same thing's going to become true of feedback-driven optimization. The same thing's going to become true of LLMs. We don't know when that's going to happen, but it will happen. So to me, there is a lot of stuff that is in academia, in research. The excitement for me, or the interesting thing for me, is how that gap has shortened between something being published and something being implemented in a production compiler near you. That to me is the sort of meta level thinking that I think has happened recently.
So thanks, Ramana. I think you said availability of compute has been a big advancement, and at least for that you need to thank architects, even if you said.
Of course.
Okay. So Abhijat, can you mention some of the recent advances that you consider very significant?
Well, I mean, actually, I don't work more in compilers nowadays, so do excuse me for a rather archaic view here. Graph lowering and polyhedral compilation would be techniques that I consider very significant, but I could be very, very off the mark at this point. But I'd like to talk about something else that would be perhaps more interesting. I have been working more in education for quite some time, and techniques from language analysis could possibly be used to specify curricula is one problem that has been attractive for me for quite some time. Fortunately, the effort was introducing competency rather than learning outcomes as a way of designing curricula. The idea of competency is to introduce a task that offers a contextual background to the education that is happening, learning and knowledge, etc., that is happening. So this is where this idea that, okay, program expression plus context is your process, that's the kind of a thinking that is something that we are trying to use, and see whether we can actually create curricula where dependency analysis can be automated. That's point one. But that's just a low-hanging fruit. More importantly, it's the learner who will get a certain context to understand why certain things are being learned. To give an example, operating systems is being taught to a information technology graduate as well as a computer engineering graduate, but the kind of tasks that information technology graduate is expected to do in practice, vis-a-vis the set of tasks that an engineering graduate is required to do are very different. And perhaps this is what we need to use to give a direction to the learning and knowledge that is imparted to the students. That's the kind of idea that is coming in from this field into education, and that is what is exciting to me. Thanks.
Thanks, Avijat. It's a very interesting perspective. Saurav, can you mention some of the recent advances that you consider significant?
Significant in my area of research. Yes. Thank you. Yeah, I'll have to give a little bit of background on what is my area of research, and so I can answer this question. So basically, the problem is that, if you look at a modern production compiler like GCC, then it has been growing in complexity over the past 30, 40 years. So for example, one statistic is that every 3 years, the code grows by 2x. So, if it was 100,000 lines of code in 1990, today it is more than 21 million lines of code. Sorry, it grows by 2 million lines of code every 3 years. So it's at 21 million lines of code today. And in fact, the reason it has grown linearly through all these 30 years is basically because the number of good engineers who can do this kind of work and who want to do this kind of work is limited. Otherwise, it should have really grown exponentially. And if you look at how much performance is left on the table vis-a-vis what we have today and what is, firstly we have covered a long distance, but still the amount of performance that's left on the table is huge if you consider the fact that even architectures can be redesigned if they have better support from the compiler. Because compiler support is not there, architects are kind of having their hands tied. So this is the problem statement, and my line of investigation, as is with many other researchers in this line, is that instead of writing the compilers by hand, can we automate a lot of this thing by kind of having a proposer, which is, think of it like an AI-based proposer that's basically proposing optimized implementations for a given specification, and then you have a verifier which checks whether the optimized implementation is equivalent to the original specification. So that's the line of work I work in, and so the two important things that I would say are, one is the huge advances in automated reasoning in formal methods like SMT solvers and all the associated algorithms. That has made verification much and more tractable over the years. I think of it as a less vocal kind of revolution that's going on. And the other thing, of course, is AI and LLMs, which is on the ability of machines to actually make good proposals. So those are the two things that I would say are the most exciting for me.
Thank you, Saurav. Before I take the next question, maybe I'll invite questions from the audience to ask to any of the participants. Would anyone like to ask questions? Anyone has any questions? No one? Everyone is sleeping? Yeah. Okay. So this is maybe you can ask some questions that people have asked online or.
Well, these are not my questions per se, but we had collected questions from people who had registered online, particularly for situations like this. So there are 2-3 questions around a particular topic. So I'm trying to paraphrase them and ask. Anybody can answer. So people say these are big pieces of software, and we sometimes get scared working with them because we aren't sure whether what we have done is introducing some more bugs rather than solving it only for a particular use case that we looked at in, let's say, a test case. So have you encountered bugs in your compilers or bugs in compilers you have worked with? If yes, then how impactful were they? When were they discovered? This is one question. And a related question is, or rather, it can be answered in the same vein, is how do modern compiler optimizations balance between performance improvements and security considerations, especially in languages that emphasize safety like Go? These are two questions on the same or similar counts.
Would anyone like to take this question?
So I'll actually, I think maybe Ramanna would be the right person to answer this question. I would just say that yes, I also feel very nervous about these things. That if I add something to a compiler, then is it a performance improvement or is it a performance regression, or is it? So these things are very complicated. And I don't think, I have done some compiler work, but mostly my work has been more about so one of my line of work has been more about verifying, like end-to-end verification of what the compiler produces. This is called translation validation. So you look at the source code and look at the assembly code and check whether they are equivalent or not. And so we built tools to do the verification because because of the line of work that I did. And we have found bugs in GCC, in LLVM, usually in the code generator phase, at the very back end phase of this. So it's not because I was working directly in the compiler, but more like I was building tools to check the output of a compiler that helped me identify these bugs.
Okay. Yeah. I can try taking this directly. How many bugs do you think are there in GCC which are open today? The bug count starts at today. If I file a new bug, I think it's in the 120,000 almost. That's where Bugzilla is. The compiler is a software product. Let's get real here. It does have bugs. it will be found. But that doesn't mean we don't find a way to make a step forward or to go ahead with it. So if you want to get involved, get involved. Each open source project, whether it's GCC, LLVM, the MLIR stack, OpenXLA, TVM, or anything else, has a bunch of new starter tasks. You can get involved with that. You can read the documentation. If you find something doesn't make sense, raise a bug, or better still, give a patch to improve it. That patch will be discussed. It will be discussed. You may find that people say that what you have written is not appropriate, or there is a different reasoning for it. But the discussion or the review is about that patch. Get involved, ask questions, write code. You will fail. There's no substitute to this. So, so I would like to take that thing of, don't be afraid that you may introduce a bug. Don't be afraid that your performance optimization is not generically applicable anywhere. Start somewhere, measure it with the best you have. Other people will come back and say where it doesn't work. Then collaborate with them to improve it so that ultimately it works. If it doesn't work, take it out and go do something else. It's okay. That's my answer to that one about performance. The second one about performance and security is, well, there many a time we look at performance and security as things which are contradictory. Sometimes you have to introduce other things to make things go slower, whereas the performance people want to make things go faster. The security people introduce a check which makes it go slower. But then we can turn to our friends in this game who are the architects and talk about how can we do something in the architecture or the microarchitecture to take care of some of these security reasons. So the answer is to get involved and do things and not be afraid of failure.
Any other panelists want to say something? Yeah, please.
Yeah, I just wanted to kind of add a little bit of what I said. So, given that the question is specifically about what bugs did you find or did you find any bugs, so I just want to give more detail on the kind of bugs that we found. So it gives you a sense of what kind of mistakes people do in, and what I have seen people do. One thing is, like for example, one of the bugs was basically that, reordering of instructions, which actually usually will not cause any failure in the execution output, but strictly speaking, it has issues if there was aliasing between the two reordering. So this kind of bugs we have found in the in the code generator phase. Another kind of thing is ignoring so undefined behavior related bugs. So you do some transformation, but it introduces extra undefined behavior. And so these are kind of bugs that people miss. And so our tools have found some bugs, but actually there is a bunch of other research literature that have found a lot of other bugs in this space, which are actually targeted towards finding bugs. Our tools are more about finding proofs. So we find a bug only once every now and then. And then sometimes we find like performance related bugs where we can see that something is being computed redundantly in the assembly code and so on. So these are the kind of bugs that we find.
Yeah, sure.
So I think just a slightly different experience. So I worked on and maintained this type checker called F-star, which you may have heard of. So it's not a compiler per se, it's a type checker. So you basically write your programs, you write specifications, and then the type checker proves that your program meets those specifications. And F-star itself has lots of bugs. If you go to the GitHub page, you'll see lots of bugs. But the scariest kind of bugs that as developers and maintainers we used to find were when somebody is able to prove false. Like then it's like the whole system is unsound. And these bugs will come up. I think we have had about 4 or 5 serious bugs that did come up, but we used to attend to them like with utmost urgency, like pulling night outs to fix the bug, and because that's really the trust level of the tool itself. Like if somebody can prove false, then you're basically done at that point. So, but still, I think our tool is open source, and we do invite contributions, and people are more than welcome to give us code patches, do pull requests on GitHub. But I think that's the nature of the software. Bugs will come up. Sometimes you prioritize them based on their severity, and I think just live with it.
Abhijit, you want to say something? Okay. Okay. So let me open this question to the other delegates from the industry. The question is about what serious bugs have you come across and how did you address the security and performance concerns? Would anyone like to please raise your hand?
Yeah, so I can answer some part of it. So I treat it as not necessarily introducing bugs as such, but a general apprehension about contributing code to the open source. So there is a general apprehension generally from the newcomers about what happens, will this be accepted, will there be problems, is this code becoming public and will my reputation go down, so on and so forth. So my answer to that, don't hesitate. You are not going to write to the upstream. You don't have the right permission. You are raising a pull request, which will be, as Ramana rightly said, which will be baked, bike shedded in the community. And not bike shedding is not on you, it's on the code. So the merits and demerits will be sufficiently discussed before it's landed upstream. So don't hesitate. If you have a piece of code, if you have an idea, just float it across. There are very good communities. For example, Node.js is super matured. They have special programs to welcome and onboard newcomers. They make sure that the newcomer, there is a special tag called first-time contributors. So they recognize you as a first-timer and they institute special people who can deal with you in that specific manner and make sure the onboarding exercise is very, very red carpet. So don't hesitate, that's my message.
Anyone else from the audience wants to respond to that question? Yeah, Prahlad.
So I think I should, Ramana said it right, this is software. It's going to have bugs, no matter what you do. If it doesn't have bugs today, tomorrow there'll be a new compiler and it'll introduce some bugs. So it all boils down to how you handle it. In many cases, you have to have a way of prioritizing it. There are these bugs which we call in MathWorks silent wrong answers, which give the wrong answers but don't give anything and don't give any indication. That's really bad. It reduces the confidence of people in the software, and this is actually there are companies there are people who depend on this software to work right. So those are the things which are high priority, these silent wrong answers. The rest of it, in many cases, you have got the technical support. You would say, okay, fine, there's something going wrong. Then you work with those folks and try to figure out ways around it, workarounds, and so on. And you have to be honest about the bugs. So you sort of end up publishing it, and this is what happens in open source, right? All the bugs are out there. And like you said, I think people should go and look at how many bugs there are in these software on which your entire operating, Linux is compiled, right? Which compiler does Linux use? Figure out the number of bugs there, but it still works. So you shouldn't be, everybody is saying, you shouldn't be afraid of bugs because they are going to happen, right? But how you handle it, how you deal with it, that does make a difference.
Thanks, Prahlad. Anyone else? Suprita, you want to say something? Okay, sure.
I mean, the more bugs you have, the more the verification community is in business.
That's the reason why I asked you.
So, yeah, my question is on a different issue, which is that, with this Gen AI kind of stuff that's happening, so is the core, is there a effort to use Gen AI in improving traditional or new age compilation processes, or is it more looked, Saurav mentioned about the super optimizing compilers kind of thing where you ask it to generate something and then you verify. But I'm asking, in the more traditional compiler way, is there any effort to use it, or it doesn't make sense?
Anyone wants to say something? Ramana, Saurav, yeah. Go ahead.
Go ahead.
Okay, I think I can give you an academic perspective, which probably you are already aware of, but maybe for the others, is that, yeah, of course, in the research community, there are efforts to kind of do different pieces of it. For example, there are efforts to do peephole optimizations automatically at the LLVM IR level, right? So, like from the so when you're doing the code generation, just before the code generation from LLVM to machine architecture, you have an optimizer, you have a bunch of rules that basically say, if you see, let's say, 2 additions in sequence, then to the same register, then you can replace it with a single addition, if it was addition with an immediate. So these kind of things are called peephole optimizations, and people have come up with automatic tools to automatically generate these peephole optimizations. So that would be one thing. Okay, but yeah, I guess your question was more about Gen AI. Yeah, so I don't know of, but these are examples of things that they are doing where there's a generator and then there's a verifier, and I imagine that they will also use Gen AI in that. But yeah, sorry, I don't know whether of any Gen AI effort.
We do better points to analysis with Gen AI.
I would be very, very suspicious about Gen AI hallucinating in alias analysis. To start with that. Okay. So that was just an off-the-cuff remark based on what you said. I think we as a community are still grappling with understanding how to use this as a tool to make ourselves more efficient. So we are starting to see the signs of AI code generator tools in the context of IDEs and development environments. So you've got GitHub Copilot, you've got Cursor, which is another VS Code derivative out there, and there are a bunch of others which are out there. The kind of things that it can do to analyze your source code and give you information about it is quite nice, but it also has a tendency to hallucinate. I've seen it make up, so I've seen some of these tools make up constructs which don't even exist in the domain-specific language that I cared about. So that's one part of it, which is the use as a tool to make yourself more efficient. The other part, which is the context, which is in the context of Gen AI to generate code, there are a couple of papers where people have attempted, I think it was a paper by Meta, where they've tried to get a code generator from an LLM. I don't know if, Shekhar, do you remember that paper? Maybe you can comment on that one. But let me just finish the thought. So there are some papers and there are some thoughts around code generators with LLMs. But if we are thinking about them in the context of reasoning based on principles from IR or from mathematics and applying them, I would say the jury is out, because ultimately it depends on whether the content that was provided to that Gen AI model when it was trained is itself correct. So that is where the challenge lies. Now, can we use it to generate test cases to give us something that gives us confidence in this and accelerate our understanding of an implementation? Absolutely, yes, today we can do that. But can it go further and do something like this where it invents an algorithm? I mean, that to me is a step too far based on where we are with the current state of the art or the little I know at this point in time.
So Uday, can I take something?
Sorry?
Can I say something?
Yeah, sure.
So it's not compiler, but I think I'll just give an example of something else that we did with Gen AI. So we have a paper in IIT coming up where it's about inferring memory safety annotations. So CheckC, for example, is a safe dialect of C, and it requires programmers to add a lot of annotations. And though there exist symbolic tools to infer those annotations, we found that they left a lot on the table. So we said, okay, can we use Gen AI to infer these annotations, LLMs basically. And it seems like a good compromise because these annotations are not trusted. Ultimately, we are going to run the CheckC compiler, that's going to enforce runtime checks also. So we did find that we were able to infer like about 85% of the remaining annotations, and in our like for about 20,000 lines of code samples. So if you can find a setting where Gen AI does not need to be trusted, but it can lessen the burden on the programmer, I think that's like, I mean, it's an ideal setting to be in.
Shekhar, you wanted to say something?
Yeah, I think there are multiple dimensions in which Gen AI can be utilized. People have tried to utilize it, and we are also trying to utilize it at different levels. So I think meta paper, which Ramana was referring to, was kind of a extreme stretch of where they want, or some people are trying to take it, where they want to kind of automatically generate optimized code and sequences and see if the code generates. So it is like extreme stretch. I don't know. There are too many challenges or doubts there in taking that direction, hallucination and validity and other things. There are something in between where it can help us using like ML Go paper is there, where it can help us in kind of, basically the problem is in a practical application compiler, there are too many dimensions under which you need to analyze and build up heuristics, and it becomes practically impossible to consider all of those. That is where your DL/ML networks can come and help you and extract information from the program and optimizations which have been done. And that is where I think there is more practical use cases, where we are also experimenting, where you can, based on the program, it can try and extract information, and you can then plug in those networks and improve your heuristics. And so that is other, and I think other use cases have been mentioned. So as a helper, where you are kind of utilizing it as a intern or entry level, where you can instruct it well so that you can accelerate and focus on the tasks which you are really interested in and spend more time in creativity, right? So it's kind of multi-level. I think the extreme like meta, I am not yet convinced as this thing, but I think other use cases are still quite useful.
Yeah, RD.
So again, my example is not really compiler's example, but there's a paper coming up in IIT ACIP from our group, where we have attempted to sort of again in the transformation space, when a system is transformed, then the data has to be migrated into the new system. And today there are not, at least not to the best of our knowledge, any tools to help map the schemas from the source to the target. So the idea was that can we use some of the techniques, machine learning techniques and program synthesis techniques, to map the source schema to the target schema, and then also synthesize the transformation rules, that is the programs to transform the data. So while we started off with program synthesis, one of the big advantages we saw with Gen AI was that we could do multimodal synthesis quite well with Gen AI. So program synthesis itself, we attempted to build on top of Microsoft Prose, where we kind of gave examples of source and target data and inferred the programs. But there are a lot of limitations, especially given the kind of data transformations that we have seen in real life from the source to the target. So for example, MS2 mappings is a big challenge. And standard techniques that Prose provides are not sufficient in order to map or infer those. Now in those cases, we realize that Gen AI kind of techniques are quite helpful in if the person or the analyst is aware at a very high level what the mappings are. If he's able to say that, oh, okay, the data looks like this on the source and like this on the target, or I think the transformation is of this nature, then with that direction, the Gen AI is able to do much better job
And so these multimodal synthesis is where we observed that Gen AI kind of techniques can be very helpful. So these are very high level problems that we are trying to solve, not really at the compiler's level. But I thought I'd just share that example. Yeah.
Thanks, RD. So I have now my next question to all the panelists. Can you describe 3 most significant intellectual challenges in this area that have not been addressed sufficiently well? If you had all the freedom and power, what would you like to do about addressing them? For example, would you like to use AI and then sit back and relax? Or are there things for which you need to use your own creativity, insight, and system building exercises? So maybe Asim?
It's a tough one. Sorry, what was the question? What are
So the question is, can you describe 3 most significant intellectual challenges which have not been addressed yet, and it's on your wish list, that I wish this was done?
Sure. So
and
I
what
think
is it that you could do?
Yeah, so I think RD's talk kind of also brought it up. I think in my existing project, using LLMs for static analysis and kind of for finding, fixing bugs, triaging bugs at scale with high quality, I think it's still an open problem. In as much as LLMs have shown promise, in as much as we have seen 1.5 to 2 minute demos of LLMs doing incredible things, I think making them work at scale with high quality, it's still quite open. And that's where our current project is coming in. And to me, it seems like programming languages techniques, the formal methods, are going to be an important part of it. We need to figure out how and what symbolic tooling to build around the models so that we can use them effectively. And to me, that's an open problem, which I think we are working on right now. In addition, so this is one problem, but maybe in the service of this problem, we also need to think about how do our tools, the formal method tools that we have been building, can we rethink them with AI in mind? So let me give an example. So for example, most of us have been working on tools, and one of the goals is to say that we should require as minimum annotations from the programmer as possible, otherwise programmers will not use it. In the mix that can do similar kind of reasoning that programmer does, is annotations really a problem? So I don't know. Maybe it's okay to say, to design a tool that takes a lot of annotations but does what it does really well, and then use AI to fill in the annotations part. And since you have your symbolic tool in the end, you don't even need to trust the AI part of it. So I think there is some scope of thinking of these formal tools with AI in the mix, and maybe the constraints that we were working with before are not really applicable. So in a way, like targeting the same problems towards high quality software, making software more reliable, but thinking of co-evolving AI and symbolic tools together so that we can do this effectively at scale and with reliability.
Saurav?
Yeah, so I'll take that question as though, like, what is the ideal world that I would like to pursue, and if I had infinite resources, then I should already been there. But I don't. So yeah, I think it's the same thing that I was just earlier mentioning as well. Like, compiler development is very important, a very critical, a very fundamental need in the whole story of the evolution of computer science, and yet it is very broken. Can we change the compiler model such that in the ideal world, the compiler model should be that some AI proposes that for this program, this is an optimized implementation. There is some verifier that checks whether it's the optimized implementation or not. If it says yes, then we store it in a database for further lookup so that we don't have to do all that computation again. And we have a huge database of optimized programs, implementations mapped from their source codes. And then when you want to, and if not, then it gives a counterexample and it helps the AI refine its search and all that. And then, you basically have an optimizer. So you write a new program and it just consults this huge database of optimizations to just do it for us. So basically, compiler writers are not writing the algorithms to implement the optimizations. Compiler writers are writing the meta level things of AI generation algorithms and verification algorithms, rather than doing the manual job of writing the optimizations themselves. Yeah, that would be the ideal word for me.
Avijat, you want to say something?
Well, I mean, there are many in the wish list and many at the ideal level, pie in the sky kind of things rather than on the ground stuff. So let me go ahead with that. As far as compilers or programming languages is concerned, one of the things I would really like to see is for every intermediate language, there is a corresponding abstract machine and an interpreter defined and done well. It's something that I really feel would be very useful and required. The required part comes in because when Manas put up those questions about from the people on the net, one of the things I noticed was everybody was looking at performance, but the correctness problem was never really brought to the table. I mean, we would want the compiler to produce correct code first and then let it be performance oriented. That's the lesson I learned when I went and presented GCC internals to the Linux kernel community, and I asked them, look guys, what do you need from the compiler people? They said, देखो आप correct code generate करो, performance हम देखेंगे. So, well, I mean, the kernel writers are pretty smart people. I agree with that side of the story, but we need to generate correct code, and correctness has many aspects to it. I mean, the whole compiler correctness, verified compiler problem is anyway open. It's hard, but at least let's try to narrow down where those problems are, and whatever problems can be done, let's get them done. That's the kind of that's the main idea I would want to put on the table. Given the current trend, given the current trends in hardware, the talks we heard in the morning from all of these people, one of the thoughts that has been there in my mind is, well, there is a hardware design space in which people construct out different architecture styles, and they have to be mapped to the corresponding program expression space. I mean, that generic problem is something that we can also start thinking about. We don't have to solve the entire problem in one go, and that never goes. I mean, it's always incremental. So, but that's one direction we can get started. That's what I feel. Perhaps it's already being done, and it's my ignorance. I concede that. I've not been in this field for quite some time, but that's one thing that I really feel we ought to do. We need to think a little more abstractly about how we can take up generic hardware description systems and map them down to the compilers or programming languages. I mean, the reason I say programming languages is because I would see computation in terms of, the way I mentioned it a couple of moments ago, program plus context is a process. So this part, context, is something that I'm not sure we have paid due attention to. It is always there. I mean, in fact, every kind of a research work that is done, there is a context that is being addressed and taken care of. That this particular context is giving a problem, and here is a paper that solves it. That's what we really do. But maybe trying to understand that would be really useful, because one way I can describe hardware, it's program with zero context. That is why it executes. We just specify the instructions, and that happens. So, whereas when we write operating systems, we actually take a lot of pain to have the context constructed and maintained properly. So, this object called context is something that we probably should start paying attention to. Well, that was the wish list. Thanks.
Ramana?
They've covered a lot of things, and okay. So I think I've got two things in my mind on my wish list. Earlier today, Girish spoke about how the DL stack is becoming deeper and deeper, or programming stacks are becoming more and more complex. There are compiler stacks in the world today where people go from Python to C++, back to Python, and back to C++. Now imagine the plight of the poor programmer who's got to debug a problem in that. My sympathies are with that person. So the area that I'm talking about, or I'm looking to draw attention to, is in our quest for performance, or in our quest for this thing. I mean, this is a wish list, right? So I can go a bit blue sky. Debugging and productivity tools are very, very important. Somewhere in our quest for producing the best abstractions, we lose and to create software which is modular, we create fragmentation in those interface layers and we drop information. Now, this makes the job of the implementer very easy, but it somewhere loses sight of the fact that the consumer of this is some programmer somewhere who needs to debug a problem. And I'll just quote Kernighan at this, which is when he said, debugging a problem is 10x more effort than deriving the original solution. So that's one area where I feel that some work or some thought needs to be put in. The second place where I think if in my wish list there was something, it is to use all the available compute resources that are at our disposal at speed of light on an SoC, on a system, on a CPU or whatever. Any Linux distribution today doesn't use all the ISA features that are in the CPU. Have we thought about program abstractions that allow us to offload the important pieces to the appropriate elements on a system that is available to us? This is an open and very long problem, and it is compounded by the fact that hardware and software develop in their own trajectories and at different paces, with different individuals being involved at different points in time. But at some point, we've got to think about the fact of how are we making the best use of the resources that are at our disposal? Can we do better than this? I think the answer is yes. And if I had infinite time and infinite energy in people, then that's what I would look to do that. That may not be what is great for, I mean, that's a personal answer. So.
Thank you very much, Ramana. You were supposed to stop at 3:30. It's already 3:33, but we'll go do a bit of JIT compilation and we'll continue for a few more minutes because I'm told that the tea has not arrived. So we still have a few minutes to kill until the tea comes. So I open the floor to the house and anybody who wants to say anything or ask anything. Yeah, I can see raised hands. Yeah, Chaitanya.
Sir, my question is that most of the discussions we had today were regarding the backend of the compiler, where the problem was optimizing the instructions we use for some particular IR. So, do you think there can be a better way to address specific problems on the front end? Like we design languages that address those domain-specific problems and do a better and then the compiler can be a bit easier to implement for that specific domain? Or do you think that all the problems boil down to the same backend and then that backend can be implemented in all languages equally?
Good question. Would anyone like to take it? Ramana has to take it.
I think I will take it. So I think there are different things here. The nature of the compiler is evolving. So some parts of the conversation today were about the backend part of it, and some of the talks were around how did we make something go better in the backend. But the languages that are feeding into that have actually evolved a lot, and it comes back to some amount of modularity in the compiler. Yes, there is a chance that we can invent a new language, and we can have we can invent the backend in conjunction with that, but we also need it to be popular for the programmers to program in it so that we have a whole bunch of inputs into this. So it's a bit of a chicken and egg problem. And a lot of times people try and in the industry we are looking at what is the most effective or what is important for bang for buck. So when you look at that kind of prioritization, it naturally gravitates towards what is most important to do, what are the languages which are important. So today that has shifted from C, C++, Fortran to also include Python, to include Java, and to include the new DSL frameworks like PyTorch or JAX or TensorFlow.
So those are the inputs that are coming to us. And at that point, you have to think about where you employ the small number of people in the compiler community to deliver the best bang for buck for the programmers who are using them. So if you connect it back to the why are we doing this? We're doing this to make life better for programmers. We have to target things that are bang for buck. And this is a really small community. We'd like more people in it, but it takes time. This is a marathon, not a sprint.
Hi, so for a bit of context, like I'm a student currently taking Professor Uday's course, and in that we're building kind of a mini compiler of our own. So our code right now is around 5-6 files at max, very small. So like then I took a look at the GCC's source code, which is around 10s to 20s of directories at the top level itself. So my question is, what's the approximate learning curve? Like how long does it take before I can realistically be one of those persons, whose commits you can see on the GCC page?
Abhijat or Ramana should answer this question. Yeah. They were behind
a really
the
tough question.
Yeah.
So GCC has a really steep learning curve. I make no bones about that. But what we see is if you have a good set of people who can guide you through the process and learn how to learn that, and you're very intentional with how you are learning it, people can start getting their code upstream and landed starting in 6 weeks. Okay. Now that is a simple task. Note that you don't start to run and rewrite the register allocator before you've fixed a small bug. And that's what I meant when I said the field of compilers is a marathon, not a sprint. And GCC makes it more of a marathon than a sprint.
Yeah. Avijat?
It took me about 2.5 years to chase a moving target. Okay. And the loss of hair that you see is also because of that a little bit that is there. But at the end, when the insights came through totally, then I realized that it's actually an error on my part. It's a benefit of hindsight. That I thought that I should really take up the entire compiler in my head and then try to understand it. Whereas it's much possible to actually do it incrementally, one step at a time, looking at various pieces one at a time. That's something that Professor Khedkar did actually. Okay, so that part makes it very easy, and it is that thing which gets it down to about 6 weeks or so. All right. More than that, I would also say that as an individual, none of us is born with the knowledge, so it's always going to be learned by each one of us. And the persistence that you exhibit in pushing that through to its final one is the one that gives you the end results. So when he's saying 6 weeks, it's for low-hanging fruits. But when you want to write the register allocator, it's going to take quite some significant amount of time that he will tell you better.
So if I may add a remark to that, because Abhijat mentioned about the GCC work that we did. We did this from 2007 to 2013. For a long time, we ran these workshops called Essential Abstractions in GCC. And our experience has been that if you didn't have, if some new person wants to start understanding GCC, there are two things. Contributing to GCC is different from understanding the structure of GCC. So our experience was that it took people somewhere between 4 to 6 months to understand the structure of GCC. But when people like Abhijat, Ramana and Samira contributed to what we wanted to do, I just set up, my job has been to set up a grand goal and find people who will find a solution to that. So these 3 people were there, key people. And our experience has been that what would take you about 4 to 6 months, that stage at the end of the workshop, participants were able to reach there in 4 days. We concluded the workshop, the title was Essential Abstractions in GCC. We concluded the workshop by showing them 27 pictures. These are the 27 abstractions. If you understand these pictures well, you can walk the maze of the GCC source. Unfortunately, we lost steam. We couldn't keep up with the newer versions of GCC. But oftentimes I come back and oftentimes I meet people who say that they still refer to our teaching material to the newer people. Although GCC structure has changed, some of the core concepts that we had identified have still remained same. So if you just type in on GCC Resource Center, IIT Bombay, you'll find all the material that we have prepared.
I will just add that I still refer new people to those material when they start. And when I said 4 to 6 weeks, it's for a decent chunk of work. Usually somebody can write a very small fix which you identify and you say this is what needs to be done. That can be done within a week. That's not a problem. But the point comes with the other point that I will make is there isn't a single person in the world who would probably know the entirety of GCC or LLVM to be able to answer that. So we have to accept that and know that we are not going to have the entirety of that technology we are working in. That's true of GCC or LLVM or MLIR or whatnot. The important thing is to be focused on the area that you're working on and to know the big picture of how it is to fit together. And then you have to draw those conclusions at that point of time. There is no serialization in this, as Abhijat was saying, that I will understand everything first and then go. That will not happen.
Maybe on this note, we can stop here and carry on the discussions over the tea. Tea has come, so let's stop here. Let me thank a lot to the panelists. It's been very useful to hear them. Let me hand over the mic to Supriya.
Thank you. So I would like to thank all the panelists for such insightful discussions. I would like to thank the audience for interesting questions and interesting discussions too. I would like to request Professor Uday to present our panelists with a token of gratitude. To begin with, Dr. Abhijat Vichare. Professor Saurav Bansal. Dr. Aseem Rastogi.
We have given to Ramana in the morning, so he doesn't get it.
I don't need
it. So it's time to take a break. Tea and snacks have been arranged outside the auditorium, just like in the morning. So refresh, relax, connect, and be back by 3:55 p.m. for some more interesting talks.
I saw you.
Thank you, sir.
The goodies are still there, okay? So come tomorrow and ask more questions. It's all right. Okay.
Our next talk is from our esteemed delegate from Fuel Labs. We have Mr. Vaivaswata Nagraj, who is a compiler engineer with more than a decade of experience working on LLVM, GCC, and proprietary compilers. He currently works at Fuel Labs and works on a Rust-like smart contract language, contributing to its compiler. His team is currently working on programming languages and compilers for blockchains, which is an open source project. Let's welcome Mr. Vaivaswata Nagraj.
Thank you for the introduction. Sorry? Thank you for the introduction. I'll be talking about programming languages and compilers for blockchains and how all of this is useful. This is what I'll briefly be talking about. I'll give a very brief background about what blockchains are, because some of you may not know what it is. And then I'll talk about how language design, decisions, and static analysis is useful in smart contracts. All right, so blockchains. At its heart, a blockchain is just a network of computers that together process transactions in consensus. In consensus means that they all agree on what should be done. And these transactions, once they are logged, they're immutable. You can't change them at that point. And a transaction can be something as simple as a money transfer. I'm sure you've all heard of cryptocurrencies. So just transferring money is a simple transaction. Or it could be something more complex, like the execution of programs that reside and execute on blockchains. These programs are called smart contracts. And because processing transactions require compute and memory resources, usually what happens is the person who is initiating this transaction ends up paying money for processing it, and that's usually called as a gas fee. All right, so what I have here is a simple example of a crowdfunding contract written in Solidity. Solidity is one of the more popular smart contract languages that runs on the Ethereum blockchain. And this crowdfunding contract, what it essentially does is, a crowdfunding campaign is one where somebody wants to do something and they ask people to contribute. And that's essentially what it is. And the person who wants to raise money deploys this contract on the blockchain, and people who want to donate money can call the contribute function there. I've not shown the details. And once the campaign is done, the owner can then withdraw all the money that's there in the contract and do whatever he wanted to do. And there's another function here, which is the refund function. So what happens here is, I'll just go into details here because this is the one that we'll talk about in the next couple of slides. So what the refund function does is it checks that so the refund is for people who have contributed but want to take back their money, which they can only do so if the campaign has ended but it has not met its goal. So it's a failure. So people will take back their money and the owner can't do anything more from that point. So what it first does is it checks that the campaign has not reached its goal. Because if it has reached its goal, then it's the owner who can withdraw all of the money. And then what it checks is that the deadline has passed. And finally, it checks that the person who's calling this function has indeed made a contribution, And if that contribution is more than 0, then it sends back, it does the actual refund. It sends money to the caller of this function, and then it updates the state to say that, okay, I've already refunded this person, nothing more to do. Don't worry if you don't understand all of the code, just the gist of it is good enough. So far so good, but there's actually a problem here. What an attacker could do is he can deploy his own contract that can interact with the crowdfunding contract. The function there is the same one that I showed before. And yeah, so what he can do is have what is called as a fallback payable function. What it means is it's a function that gets called when no other function signature matches. That's all it means. And what that function ends up doing is it just calls the refund function again. And the way this attack works is when the control reaches here and the refund contract sends money to whoever called it, it ends up here. Now the problem is there's a reentrancy. This is what is classically called a reentrancy attack. And when this happens, the whole thing keeps going in a loop until the contract itself is drained of all of its funds. And well, all of this is happening because the main problem is the state update. It's happening after sending the money. So that's when this reentrancy actually, turns out to be a bug. If the state update was done before, then this wouldn't have happened, because then that if condition would fail when it re-enters the second time. So yeah. Well, although the version that I showed is kind of simplified, something like this did happen, and it ended up costing millions of dollars. And there have been other such attacks on the Ethereum blockchain before. And you can read more about it in this paper. But there is a silver lining to all of this. What that attack did, and more such attacks, ultimately what it resulted in is people in the PL community, researchers started getting interested in this domain, because it involved a lot of money, and if you can detect these bugs beforehand, it would save a lot of money and embarrassment. So it led to a couple of new languages, well, actually more than a couple of new languages. Solidity is the language that we saw earlier. It's like the C++ of systems programming. It's the de facto language, most popular, and it's kind of a mix of C++, Python, and JavaScript. And then new ones came. Liquidity, a play on the word solidity, is OCaml inspired, and then there's Scilla, and then there are languages inspired by Rust like Sway and Move. In this talk, I'll mostly be talking about Scilla because I worked for Zilliqa blockchain earlier, and I'll be talking about Sway because I work for Fuel blockchain now. I'll talk a little bit about Move because there's a nice example that I think is interesting, and you'll find it good. All right, so how do you achieve a safer crowdfunding contract with Scilla or Sway? I mean, what design decisions did these languages take to overcome or prevent the attack that we saw earlier? So Sway has two solutions. One is a very simple library function called reentrancy guard. What the function, all you have to do is call this function anywhere or at the beginning of any of your function. And at any point, if there's a reentrancy in this function, if control enters back this function while it's already executing, then it just panics and quits. It doesn't execute anymore, so you're safe. So that's a simple solution. And then there's a static analysis solution. This is the one that students or researchers in compilers and static analysis would be interested in. So what this analysis does is it's called a CEI patterns. CEI stands for checks, effects, and interactions. So if you remember the crowdfunding example that we saw before, there were a lot of checks. Deadline has passed, the goal has not been met, and this person has contributed. There were checks, that's fine. And then what you need to then do is do the state update next. That was the bug in the code that we saw earlier, right? And then finally you do any kind of interaction with other contracts. Interaction is sending money or anything like that. So as long as the CEI pattern, the programmer sticks to this pattern, he's safe. At least he's safe from reentrancy attacks. And so what the static analysis does is whenever there's a violation of this pattern, it warns the user. And this is an example, actual example from written in Sway. And you can see here that this is the line that actually sends money, and then there's a state update. So this is violating the CEI pattern. And when you compile this program with the Sway compiler, you get a warning like this. It tells the user that you're doing something wrong. Please check your program. It's just a warning, not an error, but nevertheless useful. Scylla, on the other hand, handles this entire problem in a very different way. The language itself is designed such that reentrancy just cannot happen. And the way it does is by separating computation and communication. The idea is that you model all of your smart contracts as a state transition automata. And when there's a state transition happening, you just cannot interact with other contracts. The only way you can interact with contracts is by just sending out messages, not making function calls. And since you can't even make a function call, you just cannot have any kind of reentrancy at all. I'll show you an example next, but before I go into that, another nice design decision with Scylla is that it separates what is called pure functions. If you're familiar with functional programming, you know that pure functions are ones that don't have any side effects. So it separates pure functions from actual state transitions. So this kind of makes reading the code easier and even analyzing it or any kind of testing easier. So this is the same crowdfunding contract that's written in Scylla. This has a syntax that's similar to OCaml. What you see on the top left is, what's called as the library here is the pure part of it. It's just computations, no side effects. And then there are some parameters and the state fields being defined. And this is the state transition function. So I've again shown the same claim back function or the refund function that I spoke about earlier. And it does a very similar line of checks like, has the deadline passed, how much has this person contributed and all of that. And ultimately it does perform claim back, which is a procedure there. And that procedure, it updates the state first, and then it sends out a message. It just sends out a message, that's it. And the message is processed by the blockchain later on, but it's not a function call, so there's just no way to interact with any other contract at all. So this is, so the language itself is designed in such a way that you can't make any kind of interactions. All right, so we've so far looked at reentrancy and the problems with that, but let's look at another, a very interesting example. So how is money modeled? Money is kind of central to blockchains because, cryptocurrencies. So if you can model money well, then it's nice. And this is why I have this example of Move. What Move language does is kind of model money based on our physical currency that we have, a 500 rupee note, for example. The properties of physical cash is that only one person can own it and you can't double spend it. I can't give it to two people at the same time. And the whole idea kind of reminds you of, if you're familiar with Rust, this is pretty much Rust's Move semantics or linear logic in type systems. And what Move, actually the language Move, the name comes from Rust's Move semantics. And the way it works is, this is an example here, it's not real code, but just to illustrate. You have a coin, a resource type that's defined as a coin. And if you actually try to make two copies of the same coin, the borrow checker throws an error saying, you can't do this. On the other hand, takes a different approach. What Scylla does is, you represent money using normal integers, that's okay. But I'll give you a static analysis that will help you with whatever analysis you want to do with money. And this analysis, what it does is it tags different parts of your program. It could be expressions, it could be local variables, or state fields. basically what you do is it gives you a mapping from different parts of your program to say whether that's money or it's not money or it's some data structure that contains money and so on. So this is the result that it prints for the crowdfunding example that we saw earlier. Backers, for example, here is the table that contained how much did each person contribute. So that's a table from person to money. So that's what it says, it's a map of money. I have a couple more interesting static analysis examples, and then we'll finish. Okay, so compositional gas use analysis is, well, this is from Scylla again. And well, I told you earlier that whenever you want to execute a transaction on a blockchain, you need to pay money for it. But how much money do you pay? That depends on how big the program is or how long it takes to run the program. So it would be nice if there's a static analysis that will help you guess earlier, how much time it takes. And one thing about Scylla is that Scylla does not have general recursion or general loops. This kind of makes it easier for us to actually take a principled approach to guess, come up with a number for how much gas this program could take. I have a simple example here and a more interesting example in the next slide. So what this example does is, all it's doing is printing how much gas it takes to run that function called transition say hello. It just says A plus B, where A is the length of welcome message which is there in the state. So you have to load it, and then you concatenate it with hello, and you print it. So it's the length of welcome message and plus the length of hello. So all that is doing, it's a simple example. And this is a more interesting example, I'd say. List map is a function. People familiar with functional programming will know that a list map is a function that takes in one list. It takes a callback function. And what the callback function is, it translates an element of the list to some other type. And the list map function itself takes in this list, the callback function, and gives you a separate list where each element is mapped to another list. All right, so now, how much gas would it take to run this function? So again, this is just a polynomial that it prints parameterized by various inputs. And the result that so this is the actual result that is printed by the analysis. And what it's printing is 5a plus ab plus 11. There's actually a legend here, and A is the length of the list. Well, obviously it depends on how long your list is. And B is the cost of calling F on each element of that list. So again, how much time it takes to process each element of the list obviously matters to processing the entire list itself. So essentially, that's how much gas it's going to take. So if you can guess what your A and B will be, so that's your input to the function. If you have those inputs, then this is kind of an indication of how much gas you'll have to spend for running this function. This is another simple analysis that we have in Sway. I told you earlier about this fallback payable function. So when a function is marked as payable, that means the function can input or it can accept money. That's what it means. So if you have a non-payable function, a function that shouldn't or cannot accept money, but somebody who's calling it sends money through that function, then that's incorrect, right? You might end up losing money. So what this function does is, or what this analysis does is, whenever there's a function, you're sending money to a non-payable function and that money, the value is non-zero. So that means you might lose money, so don't do this. So this analysis just gives you a warning saying you're doing something wrong, don't do this. Well, it was mostly examples so far, so I just have 2 slides about what these languages themselves are, because I've been working on them, so let me just give you a very brief description. Scylla is pretty much based on OCaml, at least the syntax and a lot of its semantics. And its type system itself is based on systemf, and it's a very minimal language. The interpreter that we had was, the core interpreter and the type checker was just hundreds of lines of code, that's it. And the language itself is not Turing complete. As I mentioned earlier, it does not have general recursion or loops. But even though this limitation is there, practically what we found was that most contracts that we had or that were popular and used in other blockchains, we could port them to Scylla quite easily, and we really didn't find a contract or a practically used contract that we couldn't port. And Sway, this is a Rust-like language that I'm working on now. We saw examples. It has a lot of Rust features like generics, algebraic types, and polymorphism. We have a pretty extensive tooling for it. The interesting part is we don't have Rust's borrow checker. But on the other hand, we don't have garbage collection either. The reasoning for this is most of the programs that we run, they're quite really small, both in terms of how big they are and in terms of how, how much memory it takes and how much execution time it takes. But most importantly, every step of execution, the person who's running it pays for it. So even he doesn't want it to run for long. So the idea is that we don't bother with garbage collection, but at the end of it all, we just free all of the memory that was allocated. The IR itself is, well, it's quite similar to LLVM IR, but we didn't use LLVM IR itself mainly because it's easier to maintain, but more importantly, because the rest of the blockchain code was written in Rust, so it made sense to have a compiler also that was written in Rust. And our main optimization goal is code size. Gas usage also, but code size because your code gets deployed on the blockchain and it's stored on the blockchain permanently forever. So that means the smaller it is, better, or the bigger it is, the more money you end up paying for having it stored always on the blockchain. The optimization pipeline is quite similar to a traditional compiler. We have most of the important passes like mem2reg, DC, and all of that. Yeah, and finally, what does it mean to work for, be a compiler engineer or a PL engineer in a blockchain company? It pays well. Most jobs are remote. Well, a lot of people, at least like me, like that. And most projects are also open source, so you can easily showcase your work. Nobody's going to question you, and your work every day is more or less committing to GitHub every day. It's not like we have a separate tree in-house or anything like that, almost always. The cons are, well, the blockchain industry is quite notorious. There have been plenty of scam projects, so they indeed do bring a bad name to the industry as a whole. And rarely what can happen is if there's a showstopper bug, it can involve a lot of money. And well, if it happens to be a compiler bug, then I think you'll be under a lot of pressure. But again, that doesn't happen quite often. So yeah, that's it.
Any questions?
Hi. So you did not talk about any safety features in Solidity, and does it not have it? Or
it does have it. Well, when you say safety features, it's like asking, well, there's Rust and there's C++. C++ does have safety features, but it's not as strong as Rust, for example, in terms of memory safety. So I would make a similar comparison between these two also.
okay, so then why is Solidity still the most popular language, and why not?
The same reason C++ is for systems. It's always been there. It was one of the first languages that came out.
Okay, thanks.
All of these others are very new.
Do we have any more questions?
So on this fix with message passing, does it change the runtime of the blockchain from function call to message passing? Or so I mean,
in a way, yes.
Okay.
But the thing is, it's an entirely different blockchain. So
it's an entirely
different blockchain.
Okay.
So
got it.
yeah.
So the messages have to be in order, because it could happen that you process the message first. And
yeah,
then
so we end up taking a breadth first search when we process it. So that was just a standard we agreed on. All right, thank you.
Thank you, sir, for such an interesting talk on the intersection of compilers and blockchain, and with some very nice slides as well. I would like to request Professor Manas to present Mr. Vaivasvata Nagraj with a token of gratitude. Thank you. Our next talk is by our eminent delegate from Tejas Networks. We have Mr. Makaran Kulkarni, who leads the RAN innovation team at Tejas Networks, previously Sankhya Labs. With over 2 decades of experience in wireless systems, from GSM to 5G NR, he has played a key role in developing cutting-edge telecom solutions. An active member of O-RAN Standardization Forum, he is passionate about making India self-reliant in wireless technology. Please welcome Mr. Makaran Kulkarni.
It has HDMI.
Is this on? Yeah. How many of you guys were there in last Placid? Oh yeah, I mean, sir, you invited me. Probably I'm always the last one to speak, so. Yeah, because maybe I'm not the one who's a compiler guy, but probably I'm going to talk more about how we use this technology to solve some of our problems. This talk is more of continuation of what we had spoken last year, if anyone remembers, and addresses 2 of these issues. There was one question on, there's a lot of work or a lot of discussion on the back-end part, but then what are we doing to solve how programmers express? And in the panel discussion, there was a question saying that, okay, how do you see things going forward, right? So this is how we see things going forward. More of expression of in a problem domain than trying to focus on computer architecture and compiler. Compilers will solve that problem of taking the problem domain down to the required architecture. So most of the slides are too busy. They are not meant for you to consume, but more for me to talk through. So maybe pay attention to what I'm talking than the slides. So we'll do it this way. We'll just have a recap of what was the problem with radio access networks. So Tejas Networks probably is in news, and the stock price shot up more because it got the BSL contract. So we're deploying some 350K sites all across India. That's a huge number of sites and huge money. So that leaving that apart, that poses a lot of problems for us. And then we see what were our approaches in solving those problems, and then where we hit that aha moment that, okay, maybe we should do it this way, and that would solve what the problem which you are looking at. But we'll look at the problem first, right? It really doesn't involve compilers per se in the classical definition, but more of compiler frameworks. MLIR, if many of you guys are familiar with that. And from where we got this motivation, it's more from the VLSI tools. So I happen to come from Sankhya Labs, as she mentioned. We were the first DSP or fabless DSP companies in India who built our own chips for satellite and broadcast products. And we'll see that how using these compiler techniques helps us in tackling this RAM portability problem and why portability is a bigger problem for us. And beyond that, we'll see why this is, how this has an impact much in a broader sense than just trying to solve a problem of translating from model to the architecture code. And we'll see if there's a time for questions. Being the last presentation, Uday sir will be a little more forgiving and give me 5 more minutes. Just as an acknowledgement, so most of the work here has been done in collaboration with IIT Harvard. Professor Nigel Hegde is one of the advisors for us, and his students have helped us quite a lot in this work. So what's the melee in the wireless software? So as such, we as a wireless infra company we have too many product SKUs. So we have small cells, micro cells, macro cells, BBU, pooled hardware, so on and so forth, right? And add to that, okay, you have waveforms. When I say waveforms, waveform is something that radiates on the air, right? So let's not get into that part, but LT is a waveform, 2G is a waveform, 5G is a waveform kind of thing. And then you build software for all of this on all the platforms. And software efforts are prohibitive. I mean, many times people tend to think that, okay, building hardware is complex and hard, but that's actually not the not really the case. Most of the cost comes from developing and maintaining the software on all these platforms together, right? And a lot of maintenance. That's the one that takes that's a bigger challenge. And then I don't remember the delegate from MathWorks, he mentioned that maintaining the coherence between the model which you have written and the translated code that goes on these platforms, that's a much bigger challenge for us, because if someone reports that I don't get a coverage, it really means that I really need to see what I've done wrong in modeling the environment or modeling my signaling chain. And this becomes a critical path. Now, if I do find someone who understands DSP, computer architecture to put it on this, right, and software engineering, obviously it's a couple of million lines of code. It's a very small subset to hire. Probably the same problem which compiler companies find. They have a very small subset to hire, right? And so what do we say is that, can I do some sort of differentiation? Can I let the signal processing engineers solve the signal processing problem? And by some magical means, take this down to the platform which the platform engineers are building. And how do I do it was the question which was thrown to us, right? And the major challenge which we had was we were trying to reduce our dependency on one SoC vendors, because you go with one, he chokes your neck, your margins go down, and then obviously if you are dependent on the same software from one vendor, you cannot bring in your innovative stuff. But so we said that we are going to get all this done with some magical bullet which we did not know what it is, and we'll see where it led us to. So the initial days we tried some approaches. We had some sort of naive PL, I should call it PL extensions, where we said that we are going to design a programming language. I mean, the EE guys designing programming language is a laughing matter, but we said we will do something of that kind. And we came up with intrinsics to define tasks, because the main thing that brings in, disconnect from one hardware or the software running on one hardware to other hardware is that how do you do the distribution of the workload? And then we said these are the tasks, and then can I define tasks? Can I build in C++ primitives too for IPC and so on and so forth? Everything was good. The prototypes run very well, but then one of the biggest problem was traceability, right? And I intended to do this way, but where it landed up with these primitives was very hard to debug when things did not go well. And obviously there's a lot of technical debt. No one wants to rewrite the whole stack if it has been written already in C or C++, right? Then we said, okay, let's design a domain-specific language for domain-specific architectures. So why domain-specific architectures? There was some talk about how we can utilize the CPU in a maximal way, all the functionality on it. And probably we believe that that's not really the case. That's why you have domain-specific architectures where you have a subset of functions and subset of language features which intersect on that. Right? That too was more of a thought experiment. It didn't go very well. And then we said, let's go somewhere midway, try to put annotations in the code, and then pull out things from the from the existing code, and see if we can do take up this portability thing or portable scheduling on different architectures. For it's not so straightforward, especially with when the code is written in C or C++ or language that doesn't let you express the abstractions very well. Most of the attempts really worked, did not work. I mean, we can have a very long discussion on what went wrong and where we went wrong, but then that's something for another day, right? So we really hit good luck when we came across some tool called ASIP from Synopsys, and essentially this was brought in more to help us in designing code based on our ISA, because our DSP process have a different set of ISA which we believe is far more efficient than in terms of power and performance and so on and so forth. Where what they did was they allowed you to define custom instructions on custom data types, right? So int 8 might not be the data type, or you can have a complex as data type, and the custom instruction will work. And then we thought we found it, okay, this is a real cool thing, and then why it's not possible to leverage on this and build something of our own that will help me lower my expression from a very descriptive language or problem descriptive language to the machine understandable language. And at that time we came across something known as MLIR. I think it's a well-known thing to all you compiler guys, but then for us it was something new. And the idea of this framework is that, okay, you take it in a very high-level language and you progressively lower based on what work you want to do. And for us, the work was more of scheduling, how do you map the math functions, maybe loop expansion, so on and so forth. So we decided to give it a shot, and it seemed to meet a requirement. But we really didn't want to develop a DSL. Like someone correctly pointed out, the success of a language depends on adoption. And you invent a new language, it's very hard to convince even your own people to program in it. So even if that group is say 50 or 150 people, usually people don't take it up. So there is always reluctance. So we said, let's do a little differently. So what we want is generic definition. So we do modeling in MATLAB, or we used to do modeling in MATLAB. There's a gradual shift away from MATLAB for various reasons to Python. And because it allows me the same flexibility, visualization tools, and when I want to run the models, I do have very performant libraries, NumPy, SciPy, and all of them, which help me performance which is equivalent or better to what I can do with MATLAB. And one of the advantages which we see is that there is a penetration of AML techniques in communication world too, and then if I have to model any of those, then Python gives me a better advantage than what I can do with MATLAB at this point of time, right? And this came to the expression part. So express in a generic language, then derive the execution graph, and then based on your hardware description, because we are talking of multiple SKUs of platform and multiple SOCs. And to get some sort of parallelism. So parallelism is the key out here, because that differentiates the last bit of juice which you can extract from the hardware. And once you parallelize the paths, for them to converge, you need to insert some sort of magical IO ops. And once you come till there, just write passes. So these are stages, then write passes to move from one to other. And this was our general approach which we followed in developing, I would call it a DSL, but Python lowering to a platform-specific code. So few things which we kept deliberately kept away from was touching the math operations. So usually the matrix inversions or SVD and so on and so forth. We said it's better done if you understand the last bit of hardware perfectly. And this comes from our experience, because we know that from our process we could extract that highest performance only because we knew what to move where. So with this, we started designing the stuff. We had parsers, or we generated AST for Python. From there, we generated some sort of IR, and then those IR were eventually linked into some functions. So this is one thing which, this is the only slide probably that has a picture, where this is the thing that shows how our approach is similar to something that's done with the torch dynamo from PyTorch, right? So usually you would have a Python frame object that's given to the interpreter, but then in this torch dynamo thing, you do have certain compiled code. In our case, like I mentioned, these are the BLAST functions or certain functions which we don't want to write through Python. And then while you are evaluating it, the call is made to these functions to gain more of the performance. So I would skip this part. This is not. So what are the challenges when we want to do something of this kind? So few things which we stumbled for quite a long time were, how do you derive the execution graph from the Pythonic models? Because what we are essentially trying to do is, we are trying to get a parallelizing compiler for Python and try to identify implicit parallelism. So implicit parallelism is something that is important out here, right? So I think there was a talk about putting annotations to make more performant code and how LLMs can put it and so on and so forth. Probably, yeah, we don't know if LLMs can put it, but then we can infer certain kind of parallelisms based on code analysis. And the simplest ones are like for loops, and it's far more easier in the limited set of operations which we do to identify that these for loops will be parallel or they cannot be parallelized, right? The optimized scheduling is another big challenge, because that goes and even though you have written a code in a platform agnostic manner, ultimately you need to know what function or what part of this whole code is going to run on which hardware block. And if just to give an example, that the DSPs which we use, they have maybe 2 or 3 kind of DSP processors with maybe around 3 more types of hardware acceleration blocks. So how do you split this? That's in one of your translation passes. This happens to be one big challenge, right? And implicitly establishing communication channels. So once you are for parallelizing, your code has diverged, how do you bring all the things back and put it together? That's another big thing which we found troublesome in implementation. And the last thing is, not more of a technical stuff, but more of logistic, that the LLVM toolchains are not available for many of the DSP compilers. So they still go with GCC. And if we are going to follow all this, we need to come back to the LLVM IR and then take it, the backend takes it to the machine code. So that's the part where many times things get stuck. So with all this, how does it bring in portability? Because the problem statement we started with is that we have many platforms and we need one code base to rule them all. And we do all this gymnastics, and how does it really bring me in portability? So what causes non-portability are like, we can categorize them into these three items. So one is the instruction set architecture, which we can't do much about. That's the backend which has to take care of it, right? The second is the program parallelism. So optimize your execution flow, or parallelize your execution flow, parallelize for loops, similar stuff. And the I/O part, which varies from platform to platform. And if I have to get parallelism or portability, then how can I really partition the system into the graph, which can be load on each of the processing elements. So the size of the partitioning is something that really matters, because many times the same piece of code which can run on a single core might need multiple cores to execute. And how does one really handle this part, right? There are constraints from the hardware, there are timing constraints from the application, and the optimal resource allocation part which comes into picture out here. How do I communicate between all these scheduled or scheduling units? This is for the conversions. And then finally, how do I generate code for each SU? And why this is important? Because when you lower it to the last LLVM IR, from there if you take it down to each of the processor, it's a different set of instructions. So you need different backends integrated in the system to generate codes for each of these heterogeneous multi-core architectures. And finally, how to schedule these scheduling units or scheduled units on the multi-core. This is a problem more of a runtime than on a compiler. And like I mentioned, we do not deal with the ISA level parallelism, so the VLIW and SMD thing. This is better taken care while designing the processor itself than in the architecture. But still, there are few tricks which one can play in the backend, which we usually don't touch, to make this more efficient. So how does this get addressed out here? So the partitioning and splitting of the programs, putting it on the within the resource constraints, that we took care by introducing something called as a graph dialect. So this is not same as the graph dialect which TensorFlow or PyTorch talks about. These graphs are bigger processing elements than what are normal add mul sort of operations which go on there. The communication part we took care more through the extension of the MPI dialect, which is again a part of LLVM. And how to schedule, that's scheduling happens through a pass when you take the graph down to little lower forms of dialects, right? And that is all. The last line is repetition of from the previous one. So what's the significance? Why we are doing this, right? So the cost of correct software development, right? The thing, there was the stress on correctness in one of the talks, and that is enormous, and that actually surpasses the cost it takes to spin off a new platform based on different SoCs. So like Tejas being a hardware company, it's we can spin off a platform probably in 3 months or 4 months, but then moving the software on it takes the next year or more than that. And increasingly, to create differentiation in the market, we do need to have our own SoCs to and be vertically integrated, and at the same time have our own platforms. And even when you have these platforms, they are built more for different optimization metrics. Like cost is one of them, right? Power might be another, right? Or a noise floor can be one more. And you need to retarget applications on these platforms based on these metrics, which is a very non-trivial job. Because you don't know what to tune where. So this is where the scheduling passes come into picture, which schedule elements on the resources based on these metrics. And we believe that compiler frameworks and technologies, these are the things which can solve this problem, coupled with some other external inputs. I don't know, that might be from LLMs or ML or wherever it is, or in our case more of human intervention. And I think Chris Latner made this statement, right? This is the golden age of compilers. Maybe this is so. So hopefully, and maybe it will lead to solving better interesting problems and solving them. So is this the first kind of effort? No, there are a few of them which we came across while we were working on this. So one of this is the Numba MLIR. This is again a MLR-based JIT compiler, but they operate more on the bytecode than the actual Python, Python definitions. There's a Torch TensorFlow MLR, which does a very different job. XDSL is something which we found closest to what we would need, but it still doesn't get all the requirements, meet all the requirements which we had. PyXL is another for HPC, but XDSL, PyXL are the closest which we can think we work or our work is to. But there are some subtle differences which do not make them amenable easily to the RAN problem domain. So this is all I have. I think I've taken far lesser time than 25 minutes. Almost fine, yeah. So if this interests you, maybe you can reach us out. My mail address is out here. I won't be here tomorrow, but my mail address and details will be with Professor Manas and Uday sir. So that's all. Any questions maybe I can take? Or
So I have a question.
Uh-huh.
And maybe this is not so much technical in nature, the question I had.
Oh, the presentation wasn't technical at all, so I mean, we can, yeah.
So I think whatever you call this is Pythonic approach or the Pythonic way of writing your software.
Yeah.
How did you kind of get or convince your team to use it? Because you had some challenges with respect to your DSLs, and so my question was really more about because it's from MATLAB to moving to this kind of environment.
Yes.
So did you kind of think of providing some automated tools to migrate your existing software, or what was the approaches?
Okay. We didn't have to convince, the team was already moving towards Python, more to move on the NVIDIA GPUs for massively parallel simulations. So they were familiar with it. The second reason, that was the engineering part. To convince the management was easy. The cost of MATLAB license is prohibitive. It's quite prohibitive. So, you tell the engineers it's the same. See, where does it come from? They don't have to. I mean, Python provides dynamic typing, and we are doing type inferencing based on the context out here, right? So you don't have to worry about what types you are. Just tell me it's a list. Tell me what it is, right? Plus, the bigger advantage comes from the array slicing and indexing part, right? Which is, one of the things which I always do and take a presentation is show the line of one line of Python or MATLAB code and show the equivalent C code. C code spills pages over pages over pages, and it's just about picking up things from certain indices. Like you get the IQ samples, you will always take alternate ones and try to feed them for processing. So engineering wise, people are familiar with the slicing part, the dynamic typing, and good visualization, because for signal processing engineers, they really need to see what's happening out there. How does it look like? And I believe Python has a far superior graphic libraries than what we used with MATLAB earlier. I know you're from MATLAB. I'm now. This is not a MATLAB bashing thing, but I'm just telling that what made the choice, right? And for management, cost was the biggest factor. And at the same time, NVIDIA came into picture where they provided large-scale simulation platforms based on Shiona or the Ariel SDK. That helped us to move or take a call in that direction. So, do I get a T-shirt? Thank you.
Okay. Thank you, sir. It was indeed an interesting talk. It was wonderful to witness lots of interesting applications of compilers and compiler technologies on this day. I would like to request Professor Uday to present Mr. Makran Kulkarni with a token of gratitude. Thank you very much. Well, it was indeed a great day packed with loads of interesting talks, intriguing discussions. And with this, we come to the end of Placid Day 1. After the event concludes, we shall proceed for a group photo towards the main entrance of this building. Before we conclude, I would like to remind everyone about tomorrow. We have an exciting day ahead with poster sessions and breakout sessions. And I'm sure all of my friends will make the most of availability of industry delegates tomorrow. It's not often that we find so many accomplished experts together under one roof to view our posters and talk informally to students for an extended period of time. We are grateful to all of you for sparing your valuable time and for sharing your experiences and wisdom. I would now like to invite Professor Manas to conclude this event.
Well, Supriya, I'm just concluding this day as you said, we have a great event tomorrow as well. Well, first of all, of course, thanks to everybody who is wearing a red lanyard here. Without you, this event, this event depends on your arrival here, your participation here. I am sure we have troubled you a lot with preparing stuff for this amidst your busy times and schedules. So thanks a lot for preparing content and coming here, flying off here, or traveling until here. It's really, as Supriya mentioned, it's really great to see so many of you here under one roof, and it has been our pleasure to have you here. On that note, I'll also thank Professor Uday Khedkar for again initiating this event and planning it from scratch, making sure it happens successfully. So thanks to him for being sowing the seed for this event a second year in a row. Thanks to everyone in the organizing team, all the Plateau members who have been on this for several days now, and I can see them actively participating throughout the day. So thanks a lot to all of you. Without you, it won't be successful. Thanks to the eStudio team for being here and supporting us throughout the day, taking care of small things, and even helping us stream the event. That was something we did for the first time. Thanks to all the participants, of course. I'm sure you have learned a lot here, and you would probably stay in this field if you like it with much more confidence than before after today's event. I would mention one thing. In the afternoon, there was some contradiction I was wondering about, that everybody who was here said that, okay, we came to this field because we like programming, we enjoyed playing with programs, but then we are talking about systems that would lead to more and more people not having to write programs. So then what happens to your younger versions when they are interested in this area in future? But then the hope comes from this event again. All your talks, all that interesting low-level architectural features that you talked about, all the high-level abstractions that you talked about, all the challenges related to scalability, precision, and different kinds of heterogeneous hardware you talked about, and so on, problems related to correctness, verification. When so many people in the industry are working on these problems and they are seeking more people, it gives us hope that wherever the world is going, we still have a place for a lot of people who are younger versions of yourself and who still enjoy the fun in programming and creating systems from scratch, as well as developing new things for the upcoming world. So thanks to all of you again for being here. I would just conclude by saying that tomorrow morning we have again an exciting series of poster sessions. We have a 30-member strong Plateau team. Most of us have prepared posters to showcase our own work to you, so that we can also take your feedback and talk about possible directions to collaborate in future. We all will be there tomorrow waiting for you. And yes, thanks also to the colleagues who came here, the CSE department colleagues. They took a lot of interest. People are talking about this event very positively outside this hall, and it's a very good feeling, So thanks again, and have a good rest of the evening. To people who have traveled from outside, enjoy a walk near the lakeside, enjoy street food if you want, stay away from the forest, and have good night. Thank you. See you tomorrow. Yes, outside we have a group photo scheduled just immediately after, so please wait outside near the main gate.